Hello, can you hear me? Hello, hello. Hello. Hello, Antonietta. I cannot hear anything from you. Antonietta, can you hear me now?
Did you say something live? I didn't hear it. Okay.
Oh, hi, Siva.
Hi. Did you say something? I don't know. Okay.
Sorry?
Did you say something or no?
Yeah, just want to make a sound check with Antonietta.
Yeah. Okay. I know she's around as well. Yeah.
Hi, can you hear me?
Yes, I can hear you perfectly. Very good.
Adele is not around.
I guess
yet.
you can also see.
Yeah.
Perfect.
Yeah.
Okay.
Let me do one thing, because I'm going to switch connection between. Well, at some point I'm going to. Okay, so now I'm gonna switch between one connection and another connection. Just tell me if you keep hearing me with no interaction. I keep talking. You still hear me? 1, 2, 3.
Not so good.
Not so good.
Antonietta, a small comment.
Yes.
I just added the slides to Adel's talk to the website. So sometimes people like to have the slides if they missed a definition or something. So you could announce, at the beginning that people who would like to have the slides, they can get them from the website.
So which website?
Sorry?
Which website?
The symposium website.
Okay.
So it's
where
next to his abstract.
Okay. Okay, good. So slides on the symposium website next to the abstract. Great, thanks.
The same will be the case for the talk of Wendelin, but Wendelin just wrote me that he's still working on the slides.
Can you hear me?
Yes.
Okay, good.
I don't cannot hear you. I just made you co-host. So now you're able to share your screen.
Hi.
Give it a try.
Yeah, I think his audio is off. His audio is off. Yeah.
Your audio is off. I think there's no audio connected since it's not shown in the list. So in the list of participants, next to everyone, there's a sign for microphone, and for you, there's no microphone. So your AirPods are not connected, probably.
I think you should just say join computer audio or something like that.
So at the bottom left corner, there's an option for the microphone where you can play around with.
Okay, can you hear me?
Yes, very good.
Okay. Okay, great.
Okay.
Hi.
Hi.
Could you please try to share the slides now? So
Yeah.
if it works. That's good.
Perfect.
Now full screen perhaps.
So can I take, 3 minutes to mention what is the Tweedy New Researcher Award, a few words about Richard, then a few words about Adele?
Oh, sure.
Okay, how much time can I take?
What? You're the moderator. It's your choice. So
Well, sure.
everything
Okay.
that fits into 1 hour is good.
Adele, how long is your talk?
I think 45, 50 minutes. And I can also say a couple sentences about Tweedy.
Okay. So if I write something in the chat, everybody can read it.
Yes.
But now it seems I'm only connected to you, but
Oh, then you need to choose everybody in the list in the chat.
okay. Yeah, except that like this is still private to you. Okay.
Yes, this is still private. But just above the chats, you can choose, and at the very top is yes. No, that's still to me.
Everybody publicly. I did. Well, whatever. It doesn't matter.
I sent one. You can reply to that.
Antonietta?
Yes.
So Siva sent one to all, and you can press reply to this one if you click on this one, and then you should send to
Okay.
it.
What do you mean? Okay, great. Okay, so we have 1 minute. So welcome to the IMS Tweedy New Researcher Award. The award was created with funds donated by Richard's friends and family. And a new researcher is one who received their doctoral degree in one of the 5 years preceding the nomination. And the recipient of the award is Adele Javanmard, who will deliver the next presentation. Let me tell you a few words about Richard Tweedy, whom I had the honor to meet. Richard was an outstanding Australian statistician who contributed to the field of applied probability and modeling in statistical science. Richard was an international scholar working successfully both in the private sector as well as an outstanding university administrator. I met him when he was chair of the University of Minnesota Division of Biostatistics while I was a PhD student there. He joined University of Minnesota after being chair of the Department of Statistics at Iowa State University. The most fun memory that I have of Richard was at an MCM ski conference. Together with Garrett to compete in the famous ski race. And we won the prize for the team with the largest variation in the time to complete the race. Richard was not a great skier, but he was certainly very courageous. He sadly died prematurely at the age of 53, my current age. So a few words about Adele. He's an assistant professor in the Department of Data Science and Operation at the Marshall School of Business at the University of Southern California. Prior to joining USC in 2015, he was a postdoc at the Center for Science and Information with work site at Berkeley and Stanford University. He completed his PhD at Stanford, advised by Andrea Montanari, and his research interests are broadly in the area of high-dimensional statistics, machine learning, optimization, and personalized decision-making. And we will hear more about it shortly. Adele is the recipient of several awards and fellowship, including, besides the Tweedy New Researcher Award, the SNF Career Award, the Google Faculty Research Award, the Thomas Cover Dissertation Award from IEEE Society, and the Douglas Brazil Award for Junior Business Faculty, among others. So without further ado, let me leave the stage to Adele. Thank you.
Okay, thank you very much for the generous introduction. And hi, everyone. I'm Adele Javanmar from University of Southern California, and I'm really honored to present this year IMS Tweedy Lecture Award. As we all know and heard, Richard Tweedy had a very profound career, and he had made significant contribution to different domains and branches of statistics, from convergence analysis for Markov chains, from queuing theory to system theory, to Bayesian statistics, to methods for epidemiology, and the list goes on and on. It's really a great pleasure and honor to receive the award in his name. And I would like to thank the award committee for choosing me for this year's recipient of the award. Today I'm going to talk about reliable statistical inference for high-dimensional models. And this is based on several papers that my colleagues and I finished in the past few years. So I would like to start by thanking my collaborators. The first and foremost, Andrea Montanari, my former advisor at Stanford University, Yash Deshpande, who is a postdoc at MIT, and my student at USC, Mohammad Mehrabi. Okay, great. Before I continue, I would like to say that this is almost midnight in Los Angeles. So I apologize if the lighting is not perfect, but I try my best to be as energetic as possible. This is a unique experience for me, giving talk at midnight, but hopefully it will go quite well. Okay, to set the stage, we are living in the era of data deluge, where we can collect massive amounts of information and data at very fine-grained scale, very, very easily on a daily basis. And because of this eruption in data collection technology, we are also observing that quantitative methods and statistics are used in different domains, from life science to physical sciences, to economics, to finance, to business application and e-commerce, where the firms use the machine learning algorithms to improve their revenue, to better target their audience, to come up with better policy for pricing and advertising. And the list goes on and on. Probably the most relevant example to the current pandemic situation is developing drugs and vaccinations. And we know that the statistics plays a key role in this process to make sure that the drugs that are going to be delivered to the market are statistically significant in terms of improving people's health, and they can provide some virtues rather than hurting people. And we see that statistics has been used in all of these domains. I think it's fair to say that the foundation of such a widespread application of statistics has been created in the previous century by work of Ronald Fisher and many other great researchers who contributed significantly to modern statistics and also to experiment design. They basically operationalize a framework for people to do science. So this is the hypothesis-driven approach to science, where you ask some question, you formalize some hypothesis, then you test your theory on the data. And based on the outcome of your experiment, you can decide whether you should reject your theory or you fail to reject your theory. The outcome of the experiment, as we know, is not always black and white. It's not 0-1, and it contains some fair amount of uncertainty. So statistics here, the role of a statistics is to understand and interpret the uncertainty that you observe in the outcome of the experiment, and to convey your result as exactly as possible to the other people. Uncertainty in the outcomes of the experiments also make life challenging. Probably the most important challenge is the reproducibility challenge. What do I mean by reproducibility? Suppose that I have some theory and method, I run it on some data set and I find some interesting discovery. Let's say my method says that there is some association between a specific gene and susceptibility to a specific disease. So this corresponds to, let's say, in my model, one of these parameters that they have is non-zero. So there is some association between this gene and this disease. Now, this is an interesting discovery, but I want that if someone else take my theory and method and run it on a different data set, they should also be able to see the same discovery, not exactly, but at least up to a statistical error. So this is what we mean by reproducibility. And of course, we want the science to be reproducible. We don't want to be the only person who can observe our discovery. We want the other people to also be able to replicate the experiments that we have. But what we hear in the literature and the media is that the science is becoming less and less reproducible. And the media literature is full of different alarms. I'm sure that many of you have already seen many of these heads up that the science is becoming less replicable. So here I gathered a bunch of these alarms from the literature. So this is a paper by John Ioannidis from Stanford. It has a kind of provocative title that's saying that most published research findings are false. And in this paper, which is very influential and highly cited, he explained in a very simple way that what are the most common pitfalls and mistakes that people do in analyzing data sets, which leads to coming up with many, many false discoveries. The other example, for instance, is this paper, which was published in Science. And what they do in this paper is that they take 100 experiments. These are basically the studies that have been published in the top 3 journals in psychology, and they try to replicate the result of these 100 experiments. 97 of these experiments had already reported significant results. So the p-value for those individual studies were each of them less than 0.05. So they looked at 97% of these discoveries are significant, but when these people try to replicate the same experiment, only 36% of them could be reproduced. The other discoveries somehow vanished into the air. The other example is this paper published in Nature. In this paper, there is a study by Amgen, which is a company in California, and it takes 53 studies that were considered to be landmarks in basic cancer science. So these are the papers that have been published in top journals like Nature, Science, and so on. And they try to replicate, again, the outcomes of these 53 studies, but only 6 out of them, like almost 11% of them, could be replicated by Amgen. The other discoveries were not observed again in the other experiment. And probably the most relevant example, again, to the current pandemic situation is when you are doing this different phase for developed drug and vaccination to offer to the market. You see there are different phases, phase 1, 2, and it goes on. And each phase, it becomes more stringent, and you want to make sure that the drug that you are delivering is really helpful for people. So when you get to phase 3, you should be almost satisfied with your drug, almost confident. But we see that, again, in this report, 22 of these drugs that survived to phase 3 failed to phase 3. So they were considered to be significant and effective in phase 2, but when they go to the phase 3, they're not significant and they don't have that effect on that experiment. So again, you see that if you make a mistake here and you mistakenly come up with a drug and say that it can be helpful, but it's not, then it could have a catastrophic result and outcomes on people. And you see the media and literature are full of different stories trying to alert about the reproducibility crisis that we are facing. What's interesting is that we are facing this reproducibility crisis exactly at the same time that we have a good technology for collecting data. And this coincidence is not just by chance. You can argue why these two things are happening at the same time from different angles. So one argument is that because of the availability of data, the way that people are doing science has been quite shifting from a hypothesis-driven approach to data-driven approach. So in hypothesis-driven approach, which was very common in, let's say, 15, 20 years ago, people come up with some questions, some hypothesis, they collect the data, and then they test their hypothesis on the data. Based on the significance level that they get, either they reject their theory or they fail to reject. But nowadays, data is available everywhere. People are constantly exploring data, and then they come up with some interesting pattern in the data, and they ask the question. But the difference between data-driven and hypothesis-driven is that in data-driven, you first collect the data, and based on the exploration of the data, you formalize your hypothesis, and then you test your hypothesis. Data-driven approach is completely fine as far as you account for different source of bias and uncertainty in your analysis. But as a matter of fact, most people don't do this, and that's one of the reasons that we see so many false discoveries. The common mistake, which is very, very simple, is that they use the same data set to formalize the hypothesis and also to test the same hypothesis. And obviously it has bias, so it could give you many false discoveries. The other one is an interactive data analysis. So you see the same nature, but in a more subtle way. Like we know that there are many public data sets that are shared by researchers, and many different teams are testing their hypothesis on this data set. But the hypothesis that people come up depends on the data set, exploring the data set, and also the outcomes of the previous hypotheses and methods that have been tested on that one. And because of that, there is a large correlation, dependency among the hypotheses, the bias that comes from data exploration. And each of these teams might report some statistically significant finding, but when you think about the overall picture that many other teams are also trying the same data set with different hypotheses, you are facing a multiple hypothesis testing problem. So you need to control for the overall uncertainty and the false discoveries. But of course, for many of these public data sets, there is no central unit to control for the sort of family-wide error rate or the false discovery rate when many people are using the data sets. What can we do about the reproducibility crisis? Well, there have been some response from the community, like journals and conferences now require people to share their codes and data to improve the reproducibility of the results. There are different initiatives where you can submit your data and also the method and ask them whether they can also try on different data sets and make sure that the results that you found are indeed reproducible. Some part of the issue for the reproducibility crisis is the culture in the academia that people have some like urgency to publish interesting findings, and they don't report the failed experiments. Because of those culture, we also have some problem on that part, but again, I don't think there is much can be done in terms of changing the culture, at least in the next few years. The question of interest that the statistics community have been trying to answer is how to come up with new statistical methods to enhance reproducibility. And this question has initiated a long list of interesting research topics in the past few years. So I've listed some of them here, the most relevant one to this talk. So among them is the debiasing for high dimensional statistical inference that I also would spend time to explain the debiasing method. The online control of false discovery rate, which basically says that you have a stream of hypotheses coming in and you want to test this hypothesis, but you don't have any information about how many hypotheses you will have, which could be infinite number of hypotheses, and you don't know the future p-values that you get. But you want to somehow control the false discovery rate in an online manner. So this is somehow to stimulate what's happening for research findings where many people are testing their hypothesis and you don't know how many other teams would come up with new hypotheses, but you want to have some control over the false discovery rate in the infinite horizon. The other line of work is the selective inference that have different branches from post-selection, adaptive, interactive inference, the cheating, the p-hacking, data snooping. And I would like to take this opportunity to say there is an interesting seminar on selective inference organized by Rina, Will, Lihua, and Daniel. And there are many interesting talks on selective inference with the same spread. So if you can register to the mailing list, there are many interesting talks on that part as well. The other line of work is the knockoff framework for controlling false discovery rate and variable selection in high dimensions. So what I want to do in this talk is I want to spend some minutes on debiasing, the classical debiasing, and what is this method for high dimensional statistical inference. Then I will go to debiasing outside the IID world when you have adaptive data collection and introduce something called online debiasing and then see how we can use that to do inference for high dimensional time series. Okay. So the first part, the background on debiasing, is based on these papers. And let me start by a concrete example. Suppose that you have n data points. Each data point is a pair of yi, xi. Yi is sort of the response or the label of interest. And xi is the covariates or the feature vectors that you have. So as an example, you can think that yi is the glucose level of patient I, and xi is the p-dimensional feature vector that summarizes the medical record of that patient. So you can think that it's constructed based on the medications that the person is taking, the lab result, the diagnosis, the history of medication. And here I'm taking a data set from Kaggle. It's posted by Practice Fusion company. And from this data set, I'm taking 500 patients. And based on their information, I'm making around 800 features for their as the feature vector based on their medical information. This is a simple example just to convey what we want to do by statistical inference on high dimensional models. The question that I want to answer is, given this data set, I want to see what are the important features that are relevant to the glucose level. What are the features that are significantly relevant to my response of interest? And you can ask the same questions in different domains. For instance, you can, if you're working with GWAS, genome-wide association studies, you want to see what are the significant SNPs for specific disease, let's say the risk of diabetes. Or for instance, what are the important factors based on the record of people to see whether this person would reoffend to somehow gauge for the recidivism risk. The other example is that if I give you the record of the person who has applied for a loan, what are the important factors? What are the factors that are significantly relevant to see whether the loan could be paid off or not? And in these examples, I want to highlight that these are not predictions problems. Like in the first question, to understand the significant features for the glucose level, I don't want to predict the glucose level. I can easily measure that one. The question that I'm asking is more about the association. I want to see what are the statistically significant features that are relevant to my response of interest. Like is, I don't know, smoking statistically relevant to glucose level or not? Or I don't know, drinking coffee, does it have something to do with the glucose level? And I can prove it if there is some statistical significance or not. So these are the sort of questions that I want to answer. To make it a bit more concrete, suppose that we have some statistical model. So the response of interest yi is coming from some probabilistic model. So I'm assuming that there is some family of distribution which is parameterized by theta 0. Theta 0 is a vector in p dimension, it's unknown. And then once you have this family, yi is coming from this f of theta 0 condition on the features xi. And this theta 0 is somehow encoding the importance of different features, different entries of this xi in your response of interest. So what I can do is that I can try to fit a model to this data based on this family, this parametric family that they have. So in this example, I'm taking the response to be the glucose level, and I have the features. It's a high dimensional problem in the sense that the number of samples that they have, n, is lower than the number of features, p. And to recall, u was 500 and p was 800. So what I can do, for instance, is I can fit lasso estimator to come up with some estimate data I have of the model. And because of the L1 penalty, you see that here, most of the entries of my estimated model is 0, but there are some non-zero parameters. And you can interpret different coordinates of theta to somehow tell you what's the importance of that feature in predicting response y. So you get these values of theta that are non-zero. But if I do the same thing, but on a different data set. So instead of working with this data set, I resample people from the Kaggle data set and I try to fit lasso again, then I get another set of parameter estimation. If I change the population, again, I get another different set of estimation. Another question is that if you run this method on a data set and you see that some of these parameters are non-zero, how can we trust that they are really non-zero? How can we trust that there is some statistically significant association between the corresponding feature with the response of interest, with the glucose level? Because every time that they change the data set, these estimates of the importance of the variables are going to change. Okay? So how can we rely whether we found something interesting, some association or not? You can formulate this problem as hypothesis testing problem. So the null hypothesis is that the ith coordinate of my model is 0, which says that there is no association between variable I and the response of interest. And the alternative is that it's not 0. And I want to come up with valid p-values for this hypothesis testing problem. Okay? So I want to have the p-value that under the null hypothesis, they are uniformly distributed. Or I can use the duality instead of working with the hypothesis testing. I can work with the confidence interval. So I want to come up with some confidence interval for each of the individual parameters in my model so that the coverage is at least 1 minus alpha. And of course, I want the length of the interval to be as small as possible. Now, these two questions require to have some distributional characterization of the estimate theta hat if I want to answer these questions either in form of the hypothesis testing or confidence interval. And it seems to be something classic in statistics. So why is it hard? The answer is the high dimensionality of the model. So if you are in the low dimensional setting where you have a fixed number of variables and the number of samples is going to infinity, you can, for instance, take the maximum likelihood estimator and then use the large sample theory and show that it has a normal distribution. And once you have the distribution of theta hat, you can construct the p-values and confidence interval in the usual way. But when you go to the high dimensional setting where the number of features, the number of variables is much bigger than the number of samples, then the life becomes a bit challenging. First of all, you cannot directly go with the maximum likelihood estimator because here the number of unknowns parameters p is bigger than the number of observations n. So there's no unique solution to the maximum likelihood estimator, and you often require some sort of regularizer. Okay? Like the specific case for this formulation is like Lasso, where the likelihood would be the quadratic error, and this regularization would be the L1 norm. Now, if I want to characterize the distribution of theta hat, then it becomes challenging. I cannot use the large sample theory because the perturbation sort of argument that is used in the large sample theory wouldn't apply here. First of all, theta hat minus theta 0 is not negligible. And second, this regularization R is often non-smooth regularization. And because of this, I cannot use this sort of perturbation argument to show that theta hat is normal distributed. Indeed, theta hat is biased because of this regularization. Because of this regularization, the estimate theta hat is sort of having a tendency to go to the region where this regularization is small. Okay. So the question, the obstacle here is how to come up with a distribution and characterization of theta hat, your estimator, which is a regularized estimator in high dimensional setting. Okay. So the specific example is like the Lasso estimator. But if I fit a Lasso in a high dimensional model where p is bigger than n, what's the distribution of theta hat? Okay. So this is the question. And we know that this is notoriously hard, and you can only characterize the distribution of Lasso in some specific cases of design and the error. So what can we do? What's the idea of the debiasing? So let me start with the low dimensional and a very simple example. Let's focus on the linear regression, where y is given as a linear function of features. So y is x theta 0 plus noise. And in this case, if n is bigger than p, the easy estimator is the ordinary least square estimator. And we know everything about the least square. It has an explicit formulation that's given by 1 over n, the inverse of the empirical covariance x transpose 1. And the useful property of the least square is that it's an unbiased estimate of theta 0. So if I plug in for y here and I simplify, I get that the least square estimator is theta 0 plus this term, which is a Gaussian norm. Now, once you have this nice unbiased estimator and you know exactly what the distribution of this estimator is, you can compute the confidence interval and do hypothesis testing. And the sort of confidence interval that you get for each of the coordinates would have the length of like order 1 over square root n. So everything is good in the low dimensional setting. So what breaks if I go to the high dimensional setting? The first problem is that I cannot even define the least square in high dimension because sigma hat is not invertible. Sigma hat, again, to remind you, was the empirical covariance. So it's a p by p matrix, but the rank of sigma hat is n. and n is lower than p. So sigma hat is not invertible, and I cannot even define the inverse of sigma hat. So I'm stuck in the first stage. So what can we do? Let's do something similar to see what other estimator we can get for the high dimensional setting. I cannot define the least square because sigma hat inverse does not exist. But let's say I choose some matrix M, and you can take your favorite M for the moment. We then discuss what's the right choice for M. And then I define an estimator called theta hat star in an analogous way to the least square. So it's 1 over n. Now, instead of this quantity that doesn't exist, I use matrix n, x transpose y. And then I plug in for y, recollect the term, and then I get this decomposition. So my estimator theta hat star is the true model theta 0 plus a bias term plus a Gaussian error. Okay. So far, so good. The problem is that, okay, I have a bias term here, and I want to get rid of this bias. In the low dimensional case, the choice was, okay, take M to be sigma hat inverse, and then you can obviously kill the bias. But now sigma hat is not invertible, so I cannot fully make this term M sigma hat minus identity 0. I cannot get rid of this. The other problem is that theta 0 appears in the bias, and theta 0 is an unknown parameter that they would like to estimate, right? So I cannot subtract bias. But what I can do is that instead of working with theta 0, maybe I can work with another estimator of theta 0. And the choice here for high dimensional linear model is lasso. So instead of theta 0, I use the lasso estimator, and then I try to subtract bias from this theta hat star. So I get theta hat d, which is basically the theta hat star that they had, minus this is sort of an approximation of the bias that they have here. So instead of theta 0, I'm using the lasso estimator. And to remind you, what was theta hat star? Again, theta hat star was 1 over n m x transpose y. So if I plug in for theta hat star, I get this formulation. And this is called the d-biased estimator. So d here, the superscript d is for debiasing. So it's basically saying that you start with the lasso estimator. It has bias because of the L1 penalty. But I add a term to somehow compensate for the bias. But of course, when I add this term, the lasso estimator is not sparse anymore. So somehow I'm trying to transform bias into variance. And this transformation is done through this matrix M. Okay. So by this additional term, I'm removing some of the bias, but I'm adding some variance. But if I do it properly in a correct way, in an optimal way, maybe I can remove the bias, and then I can characterize the distribution of this theta at d. And once you have the distribution of the debiasing estimator theta at d, you can continue from there and construct the p-values and hypothesis testing. Okay, so the question is how to construct this matrix M. So this is the decomposition that we have. We have the d-bias estimator minus the true model theta 0 can be decomposed into a bias term and a variance term. Okay. Conditional on x, I know that this z is coming from a normal distribution, and I know exactly what the covariance of that is. And the bias, again, depends on the matrix M. So what's the right choice of M? Ideally, I want to make the bias to be 0. So I want to reduce this term. I also want to make the noise variance to be as small as possible, because the variance of the noise is determining the length of the confidence interval. Or if I'm doing the hypothesis testing, the power of the test would depend on the noise that I get here. So I want to make both of these terms as small as I can. So what I can do is that I can write a quadratic optimization for matrix M. The objective is I look at the noise term here. The variance of the noise, different coordinates, is given by M sigma at M transpose II, the II coordinate. So this is the variance of the ith coordinate, and sigma square, I don't have control over it, so I drop it in my optimization. I want to minimize the maximum variance of noise. So this is sort of minimizing the worst case confidence interval length for the coordinates. And I want to have some constraint over the bias. So I don't want the bias to be very large. So I want to control the bias. For the bias, if you look at the bias term here, you have a term m sigma hat minus identity, and then you have basically the error of Lesu. So if I use like Cauchy-Schwarz, I can take the infinity norm here and the L1 norm here. There are great results on controlling the L1 estimation error of regular decimator. So I have a control over the L1 norm of this error. I need only to control the infinity norm of m sigma hat minus identity. And this gives me an optimization to construct matrix M. How should I choose this constraint, the upper bound gamma, n, and p? It depends on the design. If you're working with a fixed matrix X, it depends on like some sort of a coherence number for the design. But if you are working with random design, the right choice for this gamma, n, and p is something of order square root of log p over n. And once you solve this optimization problem, you have the matrix M, you plug in for your d-bias estimator, and you get something nice that is unbiased asymptotically, and you know what the distribution of theta at d is. So this is the theorem that we have. Basically says that theta at d minus theta 0, it has a noise part z. The distribution of z given x is completely characterized. And the bias term that you have, you can control the infinity norm of the bias. And it's something like S0 log P over root n. What's S0? S0 is the number of entries in the parameter theta, which are not 0. So theta 0 is a vector in P dimension. So let's say P is 800 in the example of cholesterol glucose level. P was 800. But of course, you don't expect all of the covariates to be relevant to the glucose level. Probably a few of them, like 20 or 30 of them are relevant. So S0 is the number of non-zero coordinates in the model. So this is the bound on the bias, and it tells you that if this term goes to 0, so if n over S0 log P squared goes to infinity, the inverse of that, then the bias would be little o of 1. So asymptotically, you would get rid of the bias in your estimator, and then you have something very nice, which is normal. And this is going in an analogous way with the maximum likelihood estimator in the low dimension. So this is sort of a surrogate for the high dimensional case. And once you have that, you can construct the confidence interval in the high dimensional setting. And the length of the confidence interval that you get in the high dimension is, again, order 1 over root n. If you compare with the least square in the low dimensional case, it's also 1 over root n. So it's matching the length of the interval. And you can prove that this is optimal in certain ways, like in the minimax way, it's an optimal length of the interval, or if you're formulating it as a semi-parametric efficiency, it's also optimal in that way. So the difference between the length here is that in the low dimensional case, you have the inverse of the covariance. Here, if you're working with random design, you have the inverse of the population covariance. So instead of the empirical, you go with the population. Okay. And one thing that I want to highlight is that this debiasing framework that I explained does not require like the irrepresentability or beta mean condition for those people who know that are common for support recovery. Okay, you don't need those assumptions for inference. Okay, so I want to spend a few minutes on like the required sample size. Here, if you look at the theorem, what I need is that S0 log P over root n should go to 0. So it's already telling me that how many samples I need to do valid statistical inference in a high dimensional model. I basically want this quantity n over S0 squared to go to infinity. But if you think about estimation task or prediction task in high dimensional setting, the number of samples that you require grows linearly in the sparsity level. So as far as n is bigger than S0 log P, you would have like L2 consistency in your estimation and also consistency in the prediction error. So the question is that, do we really need the number of samples to grow like quadratic in S0? Or even if n is growing like linearly in S0, I can still do valid statistical inference. So all of these works on debiasing, so these are from almost 4 or 5 years ago. The analysis requires n to grow like quadratically in S0. And the questions that we were interested in, can we do like a statistical inference when you have linear growth in terms of S0? So we have 2 positive answers, and depending on the setting. So in this paper, we focused on Gaussian design. So Gaussian design means that your design metric X has IID rows, and the rows are coming from a normal distribution with covariance sigma. And then we take the debiasing approach and did some sharper analysis of the bias and variance of this estimator using a Leif-Döring technique. So this is a technique to control sort of dependency between different coordinates of the estimators. I spare you the details of the Leif-Döring technique, but using this technique, we could prove that if sigma is known to you, you can still get valid statistical inference using debiasing as far as n is bigger than S0 log p square. So this is great because n now is growing linearly in S0. And if sigma is unknown to you and you're required to sort of estimate that or do the statistical inference without knowing the covariance sigma, then apart from this condition, you also require n to grow like S of omega squared, where S of omega is the sparsity of the precision metric, the inverse of the covariance. Okay. But to keep things simple, if we focus on the known sigma, it tells you that n should be just linear in S0. The other piece of information that we got in terms of the required sample size is through something called approximate message passing, AMP machinery. So we focus on standard Gaussian design. So X has IID rows coming from standard normal. And instead of working with the classic debiasing, we define something that's slightly different. And the difference is in this coefficient. So previously it was 1. Now it's 1 over 1 minus the L0 norm of the estimator divided by n. So this is sort of a degree of freedom adjustment. And we show that if you go with this adjustment, as far as n, p, and S0 are of the same order, then you can still show that theta hat d is unbiased and follows the Gaussian distribution. Okay. So this was a rigorous proof for a standard Gaussian design. We also use non-rigorous argument based on replica methods from statistical physics to show that if you go with the same degree of adjustment in the general case where like X is coming from Gaussian design with covariance sigma, then this degree of adjustment is also important if you want to do statistical inference in a regime where n, p, and S0 are of the same order. Okay. But this is, of course, non-rigorous. It's based on replica method. So I wanted to also mention these 2 very recent work that take this degree of freedom adjustment and do some rigorous analysis and showing that if you are in the regime that, again, n, p, and S0 are of the same order, this degree of freedom adjustment is required for debiasing to give you valid confidence interval and p-value. Okay, so this was a background on debiasing. So in the few minutes that are remaining, I want to discuss how you can extend this to outside the RAD world. So what do I mean by RAD world? The setting that I explained, the debiasing, was where you have n data points. Each data point was yi, xi, and these data points were coming IID from some unknown distribution. And this is the common assumption that's usually made in the statistics community, machine learning, and so on. But in many areas of application, the data is not IID, and this IID assumption is clearly violated. So one example is when data is an expensive commodity, like in clinical trials. So in this case, you want to be very careful on how you are choosing your samples in your study. So you look at the previous outcomes of your trial, and based on the outcomes that you have, you select who should be the next sample that they want to include in my study. Basically, I want to go with the samples that are most informative about the trial. And because of that, data points that I get would be adaptively collected. They depend on the previous outcome. The other example is the time series and the panel data. So if you think about the stock market, for instance, the value of the stock that you see today, of course, depends on the previous day, and they are correlated. They are not IID. The other examples is the bandit problems, where you have an agent that's interacting with the environment. At each step, the agent takes some action, and based on the action, gets some rewards. And these rewards tell the agent that what should be the next action. Now, the observation that the agent has from the environments are basically the rewards over different times, but these rewards are dependent because each reward depends on the action that you took, and the action that you take at each step depends on the previous reward. So all of these rewards are correlated. Now, you see that this adaptively collected data setting is prevalent in different domains. So let's focus on a linear case. You have yi xi transpose theta 0 plus epsilon, but xi depends on the previous data point. So xi at time I depends on the data that you have from time 1 to I minus 1. Another question is that if you are given this adaptively collected data, can you do consistent estimation of the model? So this is the first question. And this question is quite simple, and you can observe that in different domains, you have the consistency property because the data that you collected are naturally giving you more information. So as you go on and make more samples, you collect enough information to have a consistent estimation. But the other question, which is a bit subtle, is that can we do statistical inference with adaptively collected data? And why is it challenging? Because because of this adaptive collection of the data, you have some sort of endogenous bias and correlation in your samples. And because of this bias, statistical inference becomes also more challenging. So if you think about this problem, for instance, in a high dimensional case, you have two sources of bias. One source of bias was because of the high dimensionality of the data and like the bias of the lasso or other regular estimator. The other source of bias is because the data points that you have are collected adaptively. And now it becomes more challenging to do a statistical inference. Okay, so let me tell you what happens on debiasing if you want to apply it in this setting. If you take the debias estimator, again, to recall you, this was the formulation for the debiasing, and M was constructed by this quadratic optimization. What the argument was that you have this bias variance decomposition. I try to remove the bias, and then you have this term. And since M and X are independent of epsilon in an IID setting, I can use the central limit theorem and say that it's normally distributed. But if you think about an adaptively collected setting, even if I can kill this bias term here, the noise term here is not unbiased anymore. Because again, M was constructed based on sigma hat, and sigma hat was X transpose X. So M depends on X. But since the data is adaptively collected, X also depends on the noise. And this makes that M and X both depends on epsilon. And because of this dependency, this term, the last term, also has some bias. So I have two sources of bias, one here and also the bias here because of the adaptive collection indeed. How can we deal with this? So I give you the gist of the idea on how you can deal with this part. The idea is that when you are constructing M, instead of looking all the samples together, instead of working with the entire matrix X, I use these samples in a gradual way to control the correlation between M and epsilon. So if this term, this is the noise term that I have, instead of using the same M for all the samples from 1 to N, at each step, I use a different matrix MI, but I want MI to be measurable with respect to the previous sample. So MI should be in the, let's say, sigma algebra of the previous data points so far. But if MI is measurable with respect to this, then it becomes independent of epsilon I, because epsilon I is the error that's observed at time I. This error is independent of the previous data, right? So if I can somehow make sure that MI only depends on the previous data point, not all of the xi, then I can make sure that this term here is a martingale. And once you have a martingale here, you can come up with different settings that this martingale is stable, and then you use the central limit theorem for the martingale and show that it goes under some Gaussianity assumption. So the trick here is that in construction of M, you use the samples in a gradual, in an online way. How much time do I have?
You have another 5 minutes.
Another 5 minutes. Okay, great.
Say
So,
four.
okay, so I'll go quickly over how we can come up with these matrices MI and what would be the application in time series. So I take the data points from 1 to n. I divide them into different episodes. So these are different chunks of the data. What's the length of these episodes? I take them to be generic, and then I optimize over the length of the episode. So what happens at the end of each episode, I construct a matrix M, only using the previous xi, only using the previous feature vector that we observed. And then I use that matrix to debias the future sample in the next episode. So M1 depends on the observation in episode 0, and then it's used to debias the sample in episode 1. M2 is defined based on the sample from episode 0 and 1, and then used to debias the sample in episode 2, and so on. Okay. So this way, I make sure that the MI is measurable with respect to the history, and then it's used to debias the future sample. Okay. How should I choose the length of this RL, the length of this episode? I need to compute what would be the bias of this estimator in terms of the length of the episode, and then optimize so I can make sure that the bias has the optimal rate of going to 0. So one important example of this is in high dimensional time series. So let's say you have a vector autoregressive model. You have vector in p dimension z of t, and then you have this linear form that tells you how this vector is evolving over time. So you can think of this ZT, for instance, to be different stocks, and you want to see how the value of the stocks would change over time. These matrices here are unknown in your model, and you want to estimate them. But if I tell you that one of these coordinates, like ij entry of A, is non-zero, it means that the value of stock I today would have something to do with the value of stock J, let's say tomorrow or 5 days from now. And I can, if I can do statistical inference, it means that there is some statistical significance between these two values of the stock. Now, this is, of course, an example of adaptive data collection. So what I can do is I can use the online debiasing and do confidence interval and the testing. So I can make sure that whether there is some correlation between these two or not. So I see that the time is almost done. So let me show you a numerical example on autoregressive models. So I'm taking P to be 15. I have like observations of this var D model over 60 periods, and the lag of the model is 5. And these are the histograms that you get if you do the classical debiasing versus the online debiasing. You see that these are the QQ plot and the PP plot. If I go with the classical, like the vanilla version of debiasing, there is some bias, and they are very far from the Gaussian distribution. But if I do the online version of debiasing, so I carefully control the correlation between M and epsilon, then I can make the histogram of the online debiasing to follow a normal distribution, which ensures a valid statistical inference. Okay, with that, I would like to conclude, and I would be happy to take if there is any question.
Thank you, Adel. Very interesting. I particularly like the debiasing as a way to transform bias into variance, and this leads to the classical variance-bias trade-off that we often face in statistics. And the solution that you propose is a minimax type of solution. So I have one question. There's a question from the audience as well. But my question is, has anything been done in the Bayesian approach towards solving this issue? Well, we know that Bayesian statistics was one of the interests of Richard Tweedy, together with Markov chain and Markov chain Monte Carlo methods. So in the regularization term in the lasso can be reinterpreted as a prior. And so I'm wondering whether, rather than doing minimax in the Bayesian approach.
Exactly. So the debiasing approach that I presented was mostly in terms of the frequentist version of like p-values, where you assume theta 0 is fixed and the data is random, and then you want to do inference on that one. But as you said, if you interpret like the regularized estimator to in a Bayesian setting, that the prior is coming from the regularizer, yes, you can do also statistical inference on that framework. But the usual criticism is that why the prior is like the regularizer. Like if you do the lasso estimator, why the prior is Laplace transform, right? So the L1 corresponds to the Laplace prior.
Right.
So these are two different like approach to statistical inference. So this was mostly the frequentist version.
Yeah, sure. So we do have a question from Jonas Krampe. The question is, do you know how sensitive is the debiasing technique to the choice of the tuning parameters?
How sensitive it is to the choice of? It's a very good question. So this vector, this parameter that you choose to control the bias, the way that we do in the implementation of the debiasing, if you check the code, is that we do some binary search. So we want to make this, let me go back to the optimization. So I want to make this coefficient here as small as possible. This gamma n of p, I want to make it as small as possible. But if I choose this to be very, very small, then this optimization problem is not feasible. So in implementing of the debiasing, we do a binary search, and we try to go with the smallest threshold here so that this problem is feasible. So in this way, we are minimizing bias as much as we can. We squeeze it as much as we can, and then we see what would be done in terms of the objective. But if you choose gamma not to be very small, then of course some of the biases remain there.
Good, thank you. If there's, yeah, we do have 1 minute for another question. In the time series setting, do you let the number of episodes go to infinity?
Okay, the number of episodes, yeah, can go. So the only constraint is that the length of the episode should add up to n, but you have control. So n is going to infinity, and so the number of episodes can also go to infinity. But so the only constraint is that they should add up to n. But how can I choose each of these episodes? It depends on the bias. So what we get in the paper is that, like, if you go with the exponential growth, so if let's say the length of the episode doubles each time, then it gives you the best rate for controlling the bias.
Good, thank you. Well, let's thank Adele and
Bravo.
yes.
Thank you. Doubles each time, then it
Thanks
gives you the best rate for controlling the bias.
Okay, Adele, can you stop sharing the screen? We can have the next talk. Thank you. Wendelin, can you start sharing your screen?
Yeah.
And Takashi, are you on? Can you unmute yourself?
Yes.
Thank you.
Yes, I'm ready.
Yeah.
Shall we start?
Okay, let
Just a
Wendelin share
second.
the screen.
Just a little second.
Okay. So
We can wait till Wendelin is ready, and then you can start.
yes.
Okay.
Okay, so let's start. It's my great pleasure to introduce Wendelin Berner as the final plenary speaker, except that plenary talks are given twice. So Wendelin Berner received his PhD in 1993 from University of Paris and has been a professor at ETH Zurich since 2013. He has made enormous contributions to probability theory and math physics, especially to the development of SLE, CLE, geometry of two-dimensional Brownian motion, and conformal field theory. Among the awards he has received for his work are the prize of the European Math Society, the Fermat Prize, Poria Prize, the Fields Medal in 2006, and the Gumin Prize. He's a member of the French Academy of Science, Leopoldina and Berlin Brandenburg Academy of Sciences, the Belgian Academy of Science, and has just recently become a foreign member of the Royal Society. He has provided a lot of academic service for the community, among which probably the most important for the whole math community is his work on the IMU Executive Committee, which he served from 2011 to 2018. In fact, I admire Wendelin a lot, not only for his math, but also for devoting much of his time for serving for the math community in an amazingly fair-minded way. Today, he'll be talking about how to derive the values of some divide and color exponents. So Wendelin, please.
Yes, thank you, Takashi. It's nice to see you in your Kyoto environment, I guess. And it is a very special moment to give such a talk. We are probably all in our own rooms somewhere, and it's very nice to...
Wendelin, I'm sorry, but your voice is not so loud.
Wait a second. Maybe now it's better?
Yes.
Yeah. Okay, so I was just saying that it's very nice to be all together, and despite these very special moments, and I suppose that, like for many of you, it is not so easy to do mathematics on our own in our own little rooms, and moments where we can feel that somehow we are a community and we can share things is something certainly very nice that we can cherish, and that we feel that we are not the only ones enjoying maths in our own room. Of course, this is a bit surreal because I'm speaking to an audience that has quite a few people that I can't see, and can just say that hello to everyone. The other thing is, of course, that I'm, when one gets older, one comes into the category of people that are not so used to these new modern techniques. I was already among the people who like to give Blackboard talks instead of Beamer talks to make it more lively. Probably just as an excuse to the fact that my Beamer presentations are always very dull. And so, of course, now we're in front of a laptop. It makes it even more challenging for me. I always remember when I started my PhD, how some of heroes of probability theory in the Université Paris, where I was doing my PhD, were struggling with the printout of slides that they were putting on the overhead projector. And that because that was basically the novelty at the time. I very much feel like that. Anyway, so I'll try to talk about some recent stuff. And in some sense, the goal of my lecture will somehow use the excuse of some recent easy to state percolation results that we obtained with Jason and Scott. But in some sense, the results themselves, you know, the important thing in some sense is that they're easy to state. But as such, they might not be that important. However, somehow the more general, I mean, the ones I will state are not, you know, the core of my talk. What I want to explain is to convey the fact that deriving the result reflects that one understands something new about a model, and how, you know, some new or combination of ideas and concepts show up in the proofs, and I'll try to make sense of that. So more specifically, in the first part of the talk, I will describe these type results, and I'll give a bit of background on conformal loop ensembles and things that are needed to state properly some of the results. And then in the second part of the talk, which will of course be very impressionistic because the time is limited, and each of the elements of each of the bricks that we're using could be the topic of several hours of explanation and definition if you want to make everything precise. So my goal will be just to give you some impressionistic idea of some of the tools that we use, in particular why Liouville quantum gravity shows up there and is useful. Maybe I'll try to give you a slight impression what these quantum disks are that are part of this Liouville quantum gravity story that you have maybe already heard of if you have listened to some of the talks earlier this week. And then maybe as a sort of teaser for those of you who are not so much into these two-dimensional probabilistic randomness issues, but are more familiar with stable processes, one-dimensional stable processes and their variations, such as stable growth fragmentation processes or fragmentation trees. One of the outcomes is somehow to explain that all these two-dimensional random structures that we are constructing are in some sense in a one-to-one correspondence to things that have to do with stable growth fragmentation trees. Okay, so let me start immediately. And so I'll start with the critical bond percolation on the square grid in the upper half plane. So maybe I can, just look at that. You just look at the upper half plane. So we are looking at, this is the bottom half line here of the upper half plane that I try to show with my little pointer. And each edge of the lattice is open or closed with probability 1/2, right? We're looking at the critical bond percolation model. So each edge is open or closed independently with probability 1/2. And you have a picture like that if you have a portion of the lattice, but of course it's supposed to extend all the way up there. Now, that's the usual bond percolation model, and one is interested in these models in the clusters of percolation. Now we're going to do something different, which is having to do with these divide and color models or something like that. So we are going to, once we did this first step, which is sampling this percolation, where for each of the clusters that we see here, we're going to choose at random with a coin toss, probability P versus 1 minus P, to color them in blue or red. So you end up with a picture like that, where each, you sort of see the bottom cluster here was colored blue, this one was colored blue, and this one colored red, etc. And the coin with which we color these clusters in blue and red or red is not necessarily fair. It's it could be 1/3, 2/3, right? So there's a parameter P in the model, which is what is the probability that a given cluster is colored in blue in this picture. Okay, and now what we do is that we look at the blue cluster. So we sort of forget, we erase the initial percolation picture, and then we are left with just a coloring of the sides of the upper half plane. And now we looked at the connectivity properties in the sense that, what are the paths that you can draw by, say, starting from the origin all the way to, by staying only on blue vertices. So the question I'm going to ask is, what is the size of the cluster containing the origin, of the blue cluster containing the origin for this model? And based on standard Russo-Seymour-Welsh ideas from percolation, it's sort of easy to see, to guess that the probability that this cluster will be of diameter greater than r will decay probably like a power law, first order r to the minus a when r goes to infinity, right? The probability to make it far away will decay like a power law, and there's an exponent r which depends on the parameter p. Of course, the more blue clusters there are, the easier it is to make it far away. Particularly if p is close to 1, you would expect this exponent to be very close to 0. Now, the question is, what is this exponent, right? So if you assume that critical percolation is conformally invariant in the scaling limit, which is something that everybody believes is true for the bond percolation on the square lattice, what is this exponent a? And here's the answer. If you assume that critical percolation is conformally invariant in the scaling limit, we have the explicit expression for this exponent. And of course, the formula itself, I mean, there are different type of mathematicians and different type of motivations about why to do mathematics. It goes all down to our own personal history, maybe about what we are interested in mathematics or not. I personally, I don't care about the explicit formulas. I like it when these explicit formulas reflect some deep understanding of an actual mathematical object, in that case, these percolation or percolation cluster models. And this is the fact here. There is one feature I want to say, that this dependence in P, which involves this arctangent function here, is very unusual in the context of two exponents for critical models in 2 dimensions. So it sort of suggests that something different is going on here, as opposed to the usual critical exponents that various people, including myself, have been deriving about 2-dimensional models before. So yes. One little comment I can make is that when P is very close to 0, and I'll come back to that later, when P is very close to 0, in some sense, the exponent, the optimal strategy is it costs you very much, a lot to find a blue cluster. And so the optimal strategy is just to very close to have one very big blue cluster and then color it in blue. So the limit when P goes to 0 here should be, and it is, going to give you something that is going to be close to the exponent 1/3, which is the one appearing in critical percolation. All right, so here is a simulation, like all the simulations, a few simulations I will show in this lecture. They are due to, by Jason. So here what you see is somehow a picture not in the upper half plane, but in the very, very fine mesh, but in the disk. And what you see here is somehow the blue and red boundary touching clusters that you have here. So if you think a little bit about it, the previous question is related to the number, if you look at all these macroscopic blue clusters in this picture, the big ones that touch the boundary, how many intersection points are there between these boundary touching blue cluster, very big blue clusters on the boundary, right? Because you take a point on the boundary, you ask the question, is it in a very big blue cluster here? That's the type of question we are looking at. Now, this previous result, which is a very, you can view it as a very just a specific model, specific question. This previous result is part of a more general picture. And to start with, for those of you who know this story, you can replace this Bernoulli percolation and the Bernoulli clusters that we then color. You can replace these Bernoulli percolation clusters by so-called FK percolation clusters. And FK percolation, as probably most of you know, is sort of one particularly nice variation of Bernoulli percolation, where now the edges are open and closed, but not independently from each other. So it's a dependent percolation model. And the usual way you define it, one usual way to define it, I just write it down very quickly here, is that if you define the FK percolation model in a finite box, for a given configuration, you have a certain number of connected components defined by the open edges and a number of faces that is defined by this configuration. And then you assign a weight to each configuration omega, which is proportional to square root of q, where q is a parameter in the FK model, to the power k of omega plus f of omega. So here, this is the critical FK model with parameter q in a finite box. It's known now, thanks to efforts of recent efforts of a number of people, that q equal 4 is indeed the threshold for the critical FK model to be exhibit a first order phase transition. Anyway, so this is how the picture looks like in the large scale limit. If you try to draw in different shades of gray the different clusters of FK percolation that you see, and maybe you map them on the disk because it's easier to picture, you get a collection like that. So then you first have a picture like that, and then it is natural to say, well, given what I said before, to say, well, we can try to color independently in blue and red all these FK clusters with probability P1 minus P, and then look at the blue and red clusters that one obtains. So this is the natural thing to do. And in a first paper a couple of years ago with Jason and Scott, we showed that for each of these CLE kappa prime models, there exists one special value, capital Q, such that this coloring of CLE kappa prime loops with probability 1 over Q and 1 minus 1 over Q, for one of these values, something very special happens, namely that it has a feature that can be interpreted as reflecting a nearest neighbor interaction model. So that means the obtained coloring is just a nearest neighbor interaction, meaning it is the same property that the one reminiscent of the Potts model that I described before for Q. So in particular, this shows that the only possible conformal invariant limit of FK loops is the CLE kappa prime for this particular value of Q, when Q is equal to capital Q of kappa prime. However, in this 2017 paper, we did not establish the general formula for Q over kappa prime. We just said, well, there is one. Now, in this recent preprint, we showed that the value is actually the one anticipated in the physics literature, namely capital Q is this 4 cos square of 4 pi over kappa prime. Right, so we see that out of just conformal loop ensemble configuration, which are these continuous families of loops that are defined in the model, you get, for instance, the fact that when kappa prime is 24 over 5, say, then this corresponds to some sort of notion of conformal invariant colorings with 3 colors in nearest neighbor interaction. So that would be the one supposedly related to the Potts models with 3 states. Okay, so I hope I gave you a little bit of motivation, right? So it depends on your taste. Either maybe you're just interested in saying, how on earth can one get these strange formulas for A of P, or where do these type of things come from? How do you derive this capital Q of kappa prime, equal 4 cos squared, etc. What sort of conceptual ideas come into the game when one tries to derive this model. Now I need to be slightly careful because I need to make sure I'm not running out of, be careful with time. Okay, I'm running out of time very quickly, so I have to speed up. So the second part of the talk will be trying to explain you some of the underlying ideas. So the first remark I want to make is that in both cases, the goal somehow is to look at this picture where you color, you start with a CLE kappa prime, which is a continuous model of collection of loops. Then you color them, and then you look at the interfaces between blue and red, which is these green curves that you get there. Now, in both cases, it is all about describing the law of this green interface. And once we describe this law, we can look at how much it intersects the boundary. That was going to tell us the exponents A, and some other features of its law will tell us the locality type property, the nearest neighbor type property of this blue-red coloring that I explained before. So in some sense, the goal of the game is start a CLE kappa prime, color it in blue and red with independent coin tosses P1 minus P, and just try to describe what these green interfaces are. All right, so let me immediately jump to the little movie. So this is something I'm going to show it several times. What I'm going to show you now is the following picture. I'm going to look at just the interface between in a square between the set of red clusters that hit one side, one half of the square, with the set of blue clusters that intersect the other half of the square. So let me just show you that very closely. And we're exploring this green interface slowly, progressively, so that you see how things happen. And I let it run through once. Right, so here what happens, whoops, I should have right, so what we're doing here, let me stop here. What we're doing here is we're exploring the interface between the blue. So blue is, you have blue with probability 2/3, red with probability 1/3. So you will have more blue than red. And this picture is for percolation. So we started with a critical percolation model, then we color the clusters of percolation. And then we look at the collection of blue clusters touching this half. It will have an outer boundary, which is this green, the cluster of blue clusters touching this half. We'll have an outer boundary, which is this green curve, which happens to be the same by some sort of duality feature that than the lower boundary of the set of red clusters that touch the other half of the boundary. Now, in this movie, what you see is that we are exploring this interface, and as soon as the interface hits one of the blue percolation clusters, it discovers the entire percolation cluster. It's right. So here, what you see is that you have this. So there are different shades of blue and different shades of red. They are just there so that we can differentiate between the different blue clusters, the different blue percolation clusters that then put together are forming this giant blue cluster of clusters. Now, what you see here is that when you arrived here, we discovered this blue one is there. And when we arrived somewhere here, we discovered this fairly big red one here. So we know already that the green curve will have to go, makes its way through these green-blue pockets, right? The reason why it is natural to try to look at this procedure when you sort of discover all these percolation clusters at once is that if you look at the conditional law of the remaining to be discovered picture conditionally on what we have discovered so far, well, in that case, it's pretty clear that here we're going to have independent percolation clusters that are going to be colored independently in blue and red independently of everything that what has happened before. So in particular, we sort of see that there is some sort of nice Markov property that comes into the game when we sort of decide to discover all the a percolation cluster as soon as the interfaces hits it. So if we go, say here a bit further back, right? So here at that point, we have discovered all this, and we know that we'll have to go, through all these various pockets that are, squeezed between these blue and red clusters we have already discovered. And then when we are out here, we're in open territory, we'll discover, percolation clusters that are in this area here. So let me just go the movie slowly again. All right. So this sort of shows that it's this sort of, for those of you who remember the conformal Markov property of SLE, which is the one that is, behind the scene, it is what we get here is that, the natural process that one is looking at here when you do that is actually, the discovery of a percolation cluster of one of these red or blue clusters happens at once, right? So in some sense, the discovery of a percolation clusters can be viewed as some sort of a, Poissonian event, and we can sort of view the red cluster as appearance of one of these clusters as a jump in jump process, right? And indeed, that's sort of one of the things that we did in the CLE percolation paper. If you use this idea that the stationary picture that one explores, this idea of sort of renewal of the picture after each of the jumps that correspond to the discovery of these loops, plus the fact that the loops, the law of these loops being that you discover, right, of these jumps, CLE kappa prime loops is known because it's CLE kappa prime, which is something that is well understood. This sort of gives you a description, quite a lot of information already about these green and interfaces and these blue and green objects. And in particular, is that what you get is a description of the green interface, but you are missing actually one parameter. So this tells you what the candidates are for the law of the green interface. It's a one parameter family of green laws on possible green curves, but the relation between which of these green curves corresponds to which of these values of P is actually not coming out of this approach. So we are still we are still missing one ingredient, which is exactly the status after our paper on CLE percolation for a couple of years ago. So the new trick is new input is to use additional and independent Liouville quantum gravity and additional independent Liouville quantum gravity structure on top of this entire picture of these colored CLEs that I've described here. So so before going into that, for those of you who don't not so knowledgeable about Liouville quantum gravity, I just want to make a few general browse very quickly to mention the fact that there are an amazing number of very nice developments on Liouville quantum gravity and have been taking place in these last years, but they go on at least 4 or 5 different fronts, so they can mean very different things. So here I listed 4 bullet points where different approaches to Liouville quantum gravity, which is all related to trying to define fluctuations away from you know, the Euclidean area or the Euclidean metric in the plane. So what is the random metric or random area measures that you can define in the plane that are natural from a physical perspective? And you can mention the approach by random planar maps. So this is sort of a discrete model, and I mentioned quite a number of those names that were involved in these things, lots of French people there. You have the continuous approach by mating of tree and SLE processes and conformal weldings that has been initiated by Scott Sheffield, and then you had all these very important development with Duplantier and Miller, and then further work by people like Ewen Gwyn, Nina Holden, or Shin Sun. And then you have another, you know, very recent nice work which has to do with how to define the random metric out of, you know, the GFF and after basically the second approach. So this are a recent sequence of papers by Gwyn, Miller, and Ding, Jan Ding, with Dunlap, or partially with Dunlap, Duveda, and Falconet. So there are very important things going on there. And then, of course, there's also the sort of continuum approach via somehow explicit Gaussian free field integrals, construction and computations. So these are, you know, papers by Rode, Vargas, Kupachinen, François David, and Guillaume Remy, and others. So all these things have to do with more or less, you know, the same things. And some of the challenges, of course, have to do with the fact to relate each of these items with each other. But there are somehow quite different approaches to this. So here, what we are doing is we're taking the approach of the second bullet point, which has to do with these mating of trees and the sort of geometric approach by SLE process and then weldings. And we relate it to some features appearing in the first one, which is the discrete settings, and in particular with the sort of called peeling algorithms. That is sort of one of the main tools you know, used to study those. And you can look at Nicolas Curien's webpage with his Saint-Flour lecture notes, which is basically devoted to the discrete aspects of the peeling algorithms. So very quickly, some general ideas. I just do that to see that I'm doing bad with time. Some general ideas of the proof. So the first one is what is Liouville quantum gravity? That we're going to have in mind is that there is a parameter gamma that is closely related to our parameter kappa prime, such that it is possible to define some sort of a natural random function in the plane, non-negative function in the plane that you can interpret as the exponential of gamma times the Gaussian free field. The construction of these very rough generalized function goes back to people like Hugues Krohn and Jean-Pierre Kahn, which then you can use as a density measure with respect to density, you know, with respect to morally density with respect to Lebesgue measure, even though this is of course not a regular density because the function is a generalized function, but you are able in some sense to define in the domain D a random area measure that sort of to each portion of D assigns a random area. And this is rather rough, meaning that the support of this area measure is not smooth, but it's dense in the domain D. Furthermore, when the boundary conditions of H are chosen well, having to do with so-called free boundary conditions, you can also make sense of a boundary length measure on the boundary of the domain induced by this random area measure. So meaning that you start with the Gaussian free field and you're able, in the domain, you're able to define, assign to each portion of the domain a random area, and to each, you know, arc on the boundary, you are able to assign its boundary length, which is random. Now, a simply connected quantum surface in the way devised by Scott is essentially now an equivalence class of triplets given by a domain and an area measure and the corresponding boundary length measures. But this is an equivalence class under conformal transformations. So meaning that if I distort my domain D by conformal transformation, well, you have the push forward of the measures mu and nu that are defined in this way. In some sense, when I give you an equivalence class D mu nu, it doesn't tell you what D is, because by Riemann's mapping theorem, you can always map a simply connected domain onto each other by conformal transformation. It just tells you somehow that if, how mass area is sort of distributed within the domain D, but you don't know the shape D because you are working with equivalence classes. So in some sense, what you have is a little bit like a Play-Doh, an area of Play-Doh on which there's an area measure. But the area of Play-Doh, the Play-Doh can always be stretched conformally using Riemann's mapping theorem, and you don't know which version of this Play-Doh thing which stretching of this particular area measure you are playing with, because you only see the object. Now, the important initial observation by Scott was that when you draw an independent SLE kappa type curve on top inside a domain D equipped with one of these measures, area measures, then it is possible to make sense of the quantum length, so of some length of this curve, this SLE curve that is drawn in this domain D. For a normal curve, typical curve in the domain, you can't make sense of the length defined by mu, but in the case of SLE curves, for one value of kappa and one value of kappa prime associated to the gamma you chose to start with, you can make sense of what the length of this random length of this curve is when you draw it on an independent SLE curve on top of one of these quantum gravity quantum surface. So in particular, if I superimpose, I take a domain D equipped with a area measure mu, and I draw on top of it an independent CLE kappa prime, then each of these CLE kappa prime loops gets a length. Right. So now, in particular, if you now look at the interior of the CLE kappa prime loop that you have drawn on top of this quantum surface, its interior is now going to be made of connected components, and each of these connected components will correspond to one of these quantum surfaces, which has a finite boundary length. Okay, so I have to rush. So here, let me just explain you, draw you, take my little pen and just try to draw you what I have in mind here. So we have a domain D here. And inside the domain D, you sample a CLE kappa prime. So here I'm going to draw one of these CLE kappa prime loops in here. Right? This is a loop which has double points, but not self-cross, no self-crossing. So the interior of the loop will be, everything that is sort of here. Right here. Each of the connected components of the interior of the loops is a simply connected domain, and inside of this thing, which has a finite boundary length, and each inside of this thing, you get a quantum, therefore a quantum surface, because you have a domain equipped with the trace of the area measure that you started with inside this domain. Now, the feature, which is sort of the crucial feature of, and I really need to speed up, I guess, yeah. So the crucial feature in this whole business is the following. Suppose that you draw, let me go back to the movie here. Or let's draw this picture here. Yes, do this. Suppose that we have drawn that here in this square, there is a random area measure. And suppose now that we do this discovery process. Now, the feature is the following, that each time you discover a loop, an SLE loop here, a CLE kappa prime loop, The quantum surfaces that are encircled by these loops, right? They appear one after the other, and you're looking for each of these loops as, you take the outer perimeter and you look at the quantum surface that is inscribed by it. A priori, you would guess, of course, that H has correlation. What happens to the quantum area here and what happens to the quantum area there? It's it's very much correlated, because there's a correlation between what the Gaussian free field is doing here and what it's doing there. But what happens is that along the way, when you discover the green curve, the magic feature is that the collection of quantum surfaces that correspond to the interior of each of these successively discovered CLE kappa prime loops, they correspond to a Poisson point process of certain quantum surfaces that are called quantum disks. So in some sense, one way to understand this is to say, well, a quantum disk is in some sense what is typically represents what happens inside a CLE kappa prime loop drawn on, in an ambient CLE kappa prime object, in an ambient LQG surface. And in this discovery procedure, when you do have, when you discover, these loops one after the other and look at their interior, you get exactly a Poisson point process of quantum disks in front of you. So in particular, one feature is that you start exploring a quantum disk, that means the interior of a CLE kappa prime loop, and then you explore inside there, well, you get the similar stationarity feature, meaning that all the remaining to be discovered domain that you have to continue to discover, there are going to be discoveries of Poisson point process of quantum disks. And therefore, the law of what remains to be explored is still a quantum disk itself. So I'm going, very, very, very quickly. I jumped a number of features, but the main message is that when you equip the CLE kappa prime by LQG random area measure, and when what you discover, what keep in mind when you discover these various things is not the shape of the loops that you're discovering. You just discover the inside, what is inside used as a quantum surface, right, as an equivalence class. If this is the information you collect, then you have a really nice, stationary Poisson point process discovery feature that you get there. So this is the continuous analog of some features that appear in the discrete case or in random planar maps, which is exactly, the magic and the nice features of this peeling algorithm. So this is the first result that I mentioned. The point processes of quantum surfaces that you discover correspond to a Poisson point process of certain quantum surfaces called the quantum disks. There's an additional feature, which is the more difficult one, which is to say that the surfaces that are cut out, that you leave aside when the green interface hits a boundary, they also form a Poisson point process of quantum disks. And all these features are reminiscent of results that appeared in the mating of tree paper by Duplantier, Miller, and Sheffield. And indeed, they are, derived. These are some of the CLE version of those results. So it's building on this mating of tree ideas. So as a consequence, you get that if you, instead of going from the bottom left corner to the top left, the green interface is used to define some sort of a branching tree. What you get is a variant that we can describe very explicitly, variant of this stable growth fragmentation process that can be analyzed using the tool developed for some processes, because each of the boundary length of the CLE loops that you're discovering will have some scale invariance properties. So the corresponding jumps corresponding to the appearance or disappearance of loops will correspond exactly to the jumps in a stable growth fragmentation process. Okay, I'll jump that. I just want to mention here that one of the end results is saying that if I start from a stable growth fragmentation tree, it enables you to reconstruct the couple CLE loops LQG surface of these two independent inputs together. So in some sense, what you get is that there's a natural bijection, reminiscent, of course, of the bijections that appear in the discrete planar maps, but here it all takes place in the continuum and uses completely different ideas to be derived of the couple CLE independent LQG surface. If you put them together, this is sort of isomorphic to defining a stable growth fragmentation tree. Of course, I did cut a number of corners in the statement I just made. You can look at the paper if you want to have the precise statement. Let me very briefly mention where the formulas come from at this point. So the way the formula for A of P and also for the cosinus square comes from goes as follows. It's a basic fundamental formula, and then when I see this, I always remember the nice people working on these things while I was back when I was a student, Rondoni and people like that, and of course Jean Bertoin, from whom I learned all these things. That if you take a asymmetric stable process of say alpha smaller than 1, so that's say for instance your difference between two independent stable subordinators, and you have one parameter which is the ratio between the positive and negative jumps. So it's a stable subordinator minus u times stable subordinator, or the other way around. Then if you look at this running maximum, this will be also, if you look at the jumps of the running maximum with time, this will be also a stable subordinator, right? Its jumps will correspond. And there's a nice formula that relates the index of this new subordinator with in terms of this alpha and this u. And of course, our organizing of One World probability seminars, Leif and Andreas are of course very much into these type of things. So equivalently, if you know alpha and beta, you can recover what the asymmetry parameter is, u. And this is the type of formula and inputs that you are using in the framework of these stable growth fragmentation trees that you relate to the discovery of these models that where this is the origin of these arctangent, say in A of P formulas that I started with. So somehow these type of relations having to do with how to relate an asymmetric stable, the asymmetry parameter u will be related to P in some sense, because it will tell you something about left-right asymmetry. I'm cutting lots of corners. And somehow we know alpha and beta by some other consideration, and sort of that enables you to relate the value of P to the value of alpha beta, which are related to the identification of the green interface among the one parameter family of possible candidates. Okay, so here I was trying to explain you a little bit this story about why, if you discover the percolation clusters that are touching the boundary one after the other from the left, where these how to find this stable subordinator and difference between two stable subordinators and the range of the maximum geometrically, but I don't have time to do that here. Okay. So I think that's concludes this talk. I hope I wasn't, maybe, obviously I'm not able to give you insight of all the definitions of LQG in the limited time, but I hope that for some of you, I tried to give you some motivation and gave you, some wish to try to know more about what these quantum surfaces are and how to glue them, and as a reference. So here, the papers that I talked about, I mean, the results about that I discussed is in that preprint. The previous yearly percolation papers that it builds on, is in this one, and two very, very closely related paper. Everything is with Jason and Scott. The series are here, those ones. In particular, there's a very nice story having to do with what happens when you color conformal loop ensembles for those loop ensembles that are not boundary touching and not touching itself. And so there's something intriguing going on, which has to do with the fact that the stable the asymmetric stable processes that happen, that appear there are, corresponding to an alpha between 1 and 2. So these are sort of a slightly more complicated asymmetric stable fragmentation trees, if you want that to appear there. Okay, thank you very much. I thank you for your attention, and I apologize for maybe not being very proficient in using my laptop in front of me in this little room here in my
Thank you, Ben.
place where it's raining now. Okay, thank you.
Thank you. Let's thank Ben Döring. Since the next session will start very soon, if you have questions, please send to the chat or send to Ben Döring directly. And there is an announcement from Siva, right? Siva, where are you?
Yeah, no, yeah, I'm here. You can ask a quick question. Perhaps we have another room meeting happening soon after this.
Oh, okay. So, yeah. Is there any question? Oh, yes. Do you, Andreas? Oh, what's happening?
There is one on the chat asking what about bulk exponents from Christoph Gerber.
Ah, okay.
What about? I'm sorry, I didn't hear.
What about the bulk exponents?
Yeah, well, I mean, it's of course a natural question. I mean, for all these, one has to be careful here because it's a slightly different story. The moral is that there are quite a number of other exponents one can derive here, but not all. Let's put it like this. And the bulk behavior. So, for instance, it's if you look at what I just said, these interfaces when they're in the middle, these green-blue interfaces, there will be SLE type curves. So because you are inside the domain, the influence of this P1 minus P will not be felt that much when you are inside. So it's a good question. The answer would be quite longish, but morally, indeed, you can derive not. I focused on this particular one, and that's what we did also in our paper with Scott and Jason. But again, that was more of a this was not our initial motivation. Our initial motivation was to identify the exact law of this green interface. And then once you have that, indeed, using consideration having to do with boundary conformal loop ensembles, gluing, and all sorts of things, quantum gravity ideas, actually, it is possible to derive a number of other exponents, including the bulk.
Thank you. I have some question which is not directly related to what you're talking about, but you have CLE carpet and others. Is there any work for constructing a process on that?
Yes, I mean, that's the other paper that you can, I mean, in some sense, the whole, okay, so you have two types of CLEs, the one that are boundary touching and the ones that are, where the loops are self-touching, and the one where the loops are simple curves. So this is the simple CLEs where somehow you have something which is like if you remove the holes, it corresponds like a Sierpinski carpet. And this SLE, this one that I discussed here, is the one when you remove the hole, it looks a lot more like Sierpinski gasket, touching points. So indeed, if you look at this paper here, this deals exactly with simple conformal loop ensembles in there. So what we are defining in this cycle of papers, so if you look at this one, simple CLE percolation, simple conformal loop ensembles, there is in some sense the whole structure of what would be critical percolation within the CLE carpet, right? So the law of the green curve is exactly describing what would be critical percolation living in the fractal domain defined as a CLE carpet. And the identification somehow of all these possible interfaces that you get there. Now, if you look at the QLE paper, so it's another three-letter acronym of Scott and Jason, it's sort of part of the things that we have in our drawer in terms of projects, which is that you eventually one can construct some natural harmonic functions, on the notion of harmonic functions in these carpets, and therefore make sense of some sort of a Brownian motion in the carpet. I know that's probably where you're trying to go to. But in some sense, it's a natural thing to do here. But in my personal take is that in this context, the really natural object to define in these CLE carpets is actually the percolation object. It's natural as it's a natural exercise to say, okay, I want to have a random fractal. The CLEs are natural random fractal, and then we want to have diffusion there. But the way these CLEs are defined somehow makes them much more naturally corresponding to CLE growth mechanisms that have to do with these quantum these random distances and things like that that are related somehow to these invasion percolation inside the CLE carpets that you have there. So one thing we did, just a final thing, that in that paper, what we construct, for instance, is the natural measure, the natural, quantum measure that is going to live on the carpet and on the gasket when you equip it by the natural, independent LQG object. So you have the LQG, you look at the trace of the LQG on area measure on this fractal, then you can make sense of the natural, measure living, quantum measure living in the fractal. And as it turns out, it's exactly, it's just a natural limiting measure of the growth fragmentation tree, if appropriately looked at. That is the one that has been looked at by all these people working on these growth fragmentation trees. So it's the boundary measure on the growth fragmentation tree that you had before. But that's, one natural object. And what I want to say is that this natural measure is not necessarily the natural equilibrium measure of the, of the stationary measure of the Brownian motion. The Brownian motion will live in some other special places than the percolation lives in. So, these type of things.
Thank you very much. Thank you. So I think it's already time is over.
Takashi,
yes.
Sorry. Could I propose that we move the questions? I think there are a few more into the coffee garden. There's a link that Leif put. I'll put it again here. It's like a simulated coffee room. Go there, find out what it's about. We get our cameras up. We get the opportunity to chat together in a way that it's distant, it's proximity sensitive. So please, let's take it there. Maybe you could conclude.
Okay, so let's finish. So let's thank Wendelin once again. Thank you. Okay. Siva, do you have some?
No, we are done. Yeah. So the next session.
Oh, yeah. Okay, so let's go to the next session. Thank you.
Thank you. So everyone, yes, Hi everyone, this is the last session of the New Researchers event organized by the joint venture between two Young Researchers Committee, one of the Benoît Society and one of the ANS. We talked today about the European job market, and our first speaker is Stefan de Reich from the University of Münster. He's professor of probability, and he will talk to us about how the hiring procedure in Germany works. So I ask Stefan to share. Do you have slides? Do you want to share with us?
Yeah, just give me a second.
Yeah.
Oh, it's not activated at the moment.
All right, let's see what I can do.
Now it works, I guess. Okay, can you see it?
Yes.
Okay. So
before you start, I forgot to say something. If you want to ask a question, you can just post it in the chat or wait at the end of the talk when we will open the floor for a general question. You can start now. Thank you.
Okay. So first I should say, it's a pleasure for me to present the opportunities that you actually have in Germany. And I wasn't sure what I actually should say, so now I made a few slides where I try to explain the possibilities, like the type of positions, and perhaps also to give you an idea about the funding body behind, namely the German science foundations. They have a lot of structured programs, and possibly you would like to know, when applying for some project, the background, because many of these positions are funded by the science foundations, and typically there's some structure behind. So there is like a graduate school, or there's like, there's like, it's embedded in a bigger environment. So let me first give you like the main, I guess you can't see the top line.
Not completely.
Then let's do it like that. That's okay. So, there are essentially classically two kinds of positions that you could apply for as a postdoc. You could just, it's a position typically for 1 to 3 years. In most cases, these positions are research oriented and they have third-party funding. So you can do teaching, but typically it's not an obligation. Some of these positions also come with a limited teaching, duties. So here one has to check details in the job description. And then if you are a little bit further, then you have the possibility to apply for so-called junior professorship. This is essentially something like a lectureship. The W1 is a payment scheme, if you like, salary scheme. So it's a contract which runs essentially 6 years. So it's after 3 years, there's an evaluation, and then you get another 3 years. There typically comes with a reduced teaching load in the first 3 years. This is a little bit state dependent. In Germany, we have several states and they have different regulations for these kind of positions. So typically, what would you have to do? Like in the first 3 years, you do like 1 lecture in a year, perhaps, and 1 seminar. And after 3 years, it typically increases to the teaching load of a normal professor, which is still quite okay, but which is also dependent on the university where you are employed. So then some of these professorships come with a tenure track, meaning that after 6 years, there's a possibility that you get the tenure granted, meaning that you're actually already promoted to the second step, which is a W2 professorship, which is something similar to a readership in the UK. So, and this will be then a permanent position. And well, if it's a non-tenure track position, the contract ends after 6 years. I would say that most contracts that you get at the moment are non-tenure track positions, but it depends. And from my experience, many people get good permanent positions after 3 to 5 years when they have this junior professorship, depending certainly on the candidate. So there is a third option, but this third option is more suited for someone who stayed quite a long time in Germany and who wants to have a permanent position, perhaps somewhere, but isn't that much research oriented. So it's more a position where you have some teaching duties and where you are really also typically expected to teach in German. I should say in the junior professorship level, I guess most universities would also hire you if you are not able to speak German at the moment of hiring. But in the long run, typically people like you to see that you acquire the German language, at least on a simple level. So many universities have switched to teaching the master courses in English, so there you will have no problems. And typically, essentially the research-oriented universities, they would hire also English-speaking people. So here it's no problem if you are not able to speak German. Okay. So mainly the postdoc level and the junior professorship level are the two candidates for which you should apply if you are a postdoc, I would say. And now let me just quickly go through the typical structured funding programs from the German Science Foundation. I just give this list. I mean, possibly you just put it on the web somewhere afterwards, because it just gives you a feeling once you see a job offering, what is related to it. So there are some jobs that come from the Excellence Initiative. This is actually a grant given to only a few universities with strong research groups. So typically, if the position comes from that area, there are more than the Excellence Initiatives. There are further programs, there are graduate schools, and so on. So you can be sure to get into a very active group. So the next thing that I would like to explain is the so-called collaborative research center. These are typically university-based, so it's just based at one or sometimes 2 or 3 universities, and it's a long-term research institution. It goes up to 12 years, and there's a common theme, and it's typically multidisciplinary. So if you're hired into this program, you can be sure that there's like 20 positions perhaps related to that center, and there are lots of postdocs typically in this program and also lots of PhD students. Then the priority program is a little bit similar to the collaborative research center. It's just a little bit different in the sense that it is a nationwide collaboration. So the Science Body Foundation, they just prioritize one subject, and then there are lots of projects in this subject. There are regular meetings and workshops. So you are at one university, but there will be like a meeting twice or once a year where you all meet and where you can present your results, and where typically you invite other people to present work in this area. So this is also, if you have positions with respect to the priority program, and there are some at the moment running in stochastics, it's also very nice. It's a good active environment where you can easily develop an academic career. And there's also, I mean, the research training group. This is more on, I mean, here the emphasis is on qualification of doctoral researchers. So here, most positions are for PhD students, but there are typically also a few positions for postdoc students. And here again, it's typically a very active group. Then there are typically schools, summer schools, winter schools run by these groups, and so on. So this is also a very nice structured program where you can apply. I mean, like if you see a project with job offering, then you know there's more behind. Okay, so let me finish by just saying, well, I try to show, or I try to explain or introduce the structured programs of the German Science Foundation, but there are various other job offerings. Some come from the infrastructure, so directly from the universities. There are single projects. There's another one from the ministry, BMBF, and certainly there are some people that have ERC grants. So there are lots of other funding options. And if you have to choose between different options, I really would like to say that if you feel that there is a professor at some place who's really doing good work, then you should know that even smaller places may provide a good research environment, and gifted students can also be found outside the hubs, which is perhaps a little bit different than to the well-established markets in the UK. Yes. And what you also should know is, but this is somehow quite common in maths all over the world, I would say, that many conferences and workshops can be attended even if you're not part of the structured program, which gives the money. So they are typically grants so that you can travel around and use all these meetings, and so to further strengthen your own profile and to give talks and to also attend talks. So even if you're not directly attached to the structured programs, there's lots going on which you can take part in, and so it's not exclusive, it's rather inclusive. So if you feel that it's a good option to apply in Germany, I would say do that. We are trying to get more international, and the easiest way to get in touch with or to get job offerings is to subscribe to this mailing list that I put here, and you will find also the open positions here. So it's the same list. Here you get the emails once they come to this, once they are sent to the moderator, and here you can directly see the open job announcements at the moment. So you will see the most of them are advertised in English, some are still in German. You will also find some advertisements for jobs in the UK or Italy there. So you can just Google the STNet and just have a look. Actually, that's all that I wanted to say, and I hope that this wasn't too much and this was in the line of what was intended by the organizer.
Yes, thank you very much. Can we open the floor to any questions from the audience? You can just unshare your screen so the next speaker in the case can start already to. Of course, we will upload all the slides that you're watching during this session at the end in the webpage of the course. Okay, if there is no question, I have a question. How is it expected from your point of view to change the job market in Germany due to COVID-19 crisis? So the economic crisis that is actually we are living in a little bit in this period.
Yeah, I mean, that's a good question, certainly. At the moment, we don't feel it in the sense that we have still the programs running. So somehow the money is flowing in and there are lots of offerings. So there's no change at the moment, but in the long run, certainly it's unclear how the government will change this. And once there's less money, and I think then this will be the same for all countries, once there's less money to distribute, this might also affect the science market. Right, but at the moment we don't see it. So everything is just running, and there are this at the moment, I should say, at the moment, certainly we are affected by the COVID, but the job market per se hasn't changed. So all there's no reduction in funding at the moment, and everything is running.
Okay, we have also a question from the audience, from Madi. I don't know if you want to just do the question directly or just I read it out in the chat. Could you tell us about jobs which comes with promotion from W1 to W3? So a little bit.
From W1 to W3.
Yeah.
Well, this is not that common. So typically, the standard thing would be to get the promotion to the W2. The W3 is some option that you always have. I mean, you can always apply for a W3 position. It's just not automatically included typically in the W1. There might be some places that do that, because like in the southern German states, some universities, they only have W3 positions. So they distinguish two kinds of W3 positions though, and then they certainly would do a tenure track and you would directly get the W3 position. But I should say you can check that on the internet. The salary schemes aren't that different, and it's always possible to negotiate some money on top. So there are like people that are on W2 positions that get a better salary as people that are on a W3 salary, because it's just they had better negotiations, for instance. So it depends very much on the state, and it also depends very much on the negotiation. So, but the W1 position typically gives you only the upgrade to the next position, which would be the W2 in the northern states, and in the southern states, the W3 on this lower level. So even though you won't find this in the payment scheme, there is a distinction also in the south between the higher level and lower level advanced professorship.
I have to interrupt you. Sorry, we are a little bit running out of time already. There is another question from Raymond in the chat. You could just answer it directly in the chat, or if you all like, we can all meet after this session in the coffee garden and have more conversation with a little bit more calm. Let's pass to our next speaker in the meantime. She's Amos Berat. She's professor of statistics at the Imperial College in UK, and therefore she will talk to us about the structure of the UK job market at the moment and in general. So Amos, the floor is yours.
Thank you very much, Emma. Can you all see my screen now? Can you see my PDF? Or? Yes, okay. Perfect. Okay, brilliant. Thank you. Okay, thank you very much for the invitation. It's a great pleasure to talk to you about the career paths in the UK. So I'm originally from Germany, actually, and I did my first degrees in Germany, but then I did part of my degrees like a master and a PhD in the UK. I worked a little bit in Denmark as well, and then I have been in the UK for 9 years, really, on various positions now at Imperial College. So I would like to now talk a little bit about the structure in the UK in mathematics and statistics. So typically, obviously, you have to do your PhD. In the UK, this typically takes 3 to 4 years. It's now closer to 4 years, I would say. So most of our scholarships would fund PhD students for up to 4 years to complete their PhD. And then actually it looks quite similar to what you've seen from the German system. It's also then very common that right after the PhD, people would apply for a postdoctoral position. You could, in principle, obviously apply already for or an assistant professorship. No one will stop you from doing this, but we see that most people would probably have at least a year or a couple of years of postdoctoral experience. So when it comes to postdoctoral positions, there are various positions out there. They are the positions which are essentially directly funded through the university. So there are essentially certain fellowships which are just advertised on a yearly basis. Okay, so then you just have to look for the open calls by the universities, and then you apply directly for a postdoctoral fellowship in mathematics or in statistics. Then there is the other route, which is essentially funded through external grants. In the UK, this is mainly EPSRC, so this is the Engineering and Physical Science Research Council, but there are other research councils as well. And often this works that more senior academics might apply for a big grant to run a research project, and this might involve 2 or 3 postdoctoral researchers. And then as soon as this grant has been approved, then the universities would then advertise for these postdoctoral positions. So these kind of positions can also really come up any point in time during the academic year. So the ones, I would say, the yearly fellowships offered by the universities directly are typically advertised, so that would start sometime in late summer or at the start of the academic year, which in the UK typically starts in October. Whereas the other postdoctoral positions could in principle start at any point in time, depending on how the grant was essentially structured. And then there are the more, I would say, independent postdoctoral position, where actually the fresh PhD student or the current postdoc would actually just apply for their own funding. Okay, so they can really just design their own research project and can apply for their own postdoctoral or early career fellowship. Okay, and then obviously you're the one who designs and decides on the project. So I think that's a very nice option to keep in mind. Many of, I would say, the postdoctoral positions funded through the universities directly would also be kind of open in terms of topics, right? But if you join obviously on a big grant, then there would be, you know, a topic associated with that grant, and then you would be expected to at least partially work within the lines of this kind of grant agreement. Okay, so it would be, as I said, quite common that you would be joining on a postdoctoral position for, I would say, at least a year, maybe 2 years, and then often people look for more permanent positions afterwards. There are several routes in the UK how this is structured. So it very much depends on the university. So there's what I would call the more traditional UK system. I call it here Model 1 on my slides, that you would be joining as a lecturer, and then you can be promoted to a senior lecturer and a reader and then a full professor. This is not a tenure track really. So this is essentially a kind of career structure where you would be joining as a lecturer, and at the beginning you typically have a probation period. So now I would say it's quite common that this probation period might be 3 years, but it obviously depends also on your previous experience and so on. During that probation period, obviously it's not a permanent position yet. The university would tell you what the criteria are out of probation, and after that, after the probation period, your contract essentially becomes permanent, okay? And the important thing to remember here is that you could, in principle, so your lecturer position can then just become a permanent lectureship, and you could stay there until, you know, you retire in some sense, right? So there is, it's not that it's that you get automatically promoted. It's not this kind of up or out system what you typically have in this kind of, in the more traditional tenure track, okay? So you can join, and obviously if you have, you know, more significant experience already, you don't have to join as a lecturer, right? So you could join as a senior lecturer, or you could join as a reader or a full professor, right? So, and the universities would advertise, you know, at which level they are looking for somebody, and but then they're typically restricted to also really hire at that level. So if they advertise for a lecturer, it's quite, I mean, it's pretty much impossible to then join as a full professor, right? So, but sometimes they, you know, advertise for a lecturer, a senior lecturer, and then it depends on your qualification and at which level you could join, okay? And then there is what I would call the more, I call it the American system, or the classical tenure track system. Some UK universities now have the system that you would be joining as an assistant professor, and it's a classical tenure track. So at the end of your tenure clock, you will be evaluated, and then either you get promoted to the associate professor, or your contract will be terminated, okay? So, so personally, I mean, I'm at Imperial in mathematics, we have the old UK structure. So personally, I didn't experience this kind of tenure track position. I experienced this position where you have a probationary period and then you kind of stay on. And I should say, obviously, in the UK system, you can, you know, promote it to the next level. There's typically every year there's a promotion round where people can apply. Okay, so you don't have to wait for a position to open up. Okay, so in every year you can essentially, you know, if you feel like you're ready, you can talk to your head of department and can ask, apply for promotion, and they will essentially, you know, advise you whether it's the right time to apply. And obviously, if there's an open position advertised, you can also, you know, apply as an internal candidate for the open position. So these are obviously the two kind of career options you should keep in mind. Similar to what was just presented for the German system, we also have essentially a new career path which focuses more on teaching. So if people want to focus more on teaching, they can join also as a kind of lecturer, focusing more on teaching. This career path is rather new, I would say. So you can actually, the idea is that you can go through all the levels, right? So you could be kind of a senior lecturer focusing on teaching. And my understanding is that you could be promoted up to full professor focusing on teaching, but this is still kind of a newer career structure. So most people who are on these positions are still at the, I would say, lecturer stage. Okay, so this is something we have to kind of see, you know, how this career path develops. What I've seen at Imperial is that, for example, some people join as a teaching fellow for a year, and then afterwards they switch to a more traditional lectureship, and then they are on the traditional path. Okay, so obviously, you know, you can apply to switch path if you like to do that. So this is also an option. So if you just concluded your PhD, you know, it might be a good opportunity to just join as a teaching fellow, you know, get to know the department, and then next year also apply for lectureship. So this is really a nice opportunity to have. Shall we, I don't know, shall we discuss some questions first, or shall I comment on the impact of the pandemic?
Yeah, before that, we have actually a question that is directly on the career path structure. The first question is, what is the criterion of choosing Model 1 and Model 2? So
well, the universities decide, right? So it's not up for the candidate to decide, right? So if you choose the university you want to apply to, and they will tell you which structure they have, right? So and you know, even within the university, it might not be the same system. So say at Imperial, you know, in mathematics, we have the traditional UK style, whereas at our business school, where you might want to be, if you do financial math or statistics, financial econometrics, you would be on the American tenure track system. So, you know, we even have two different structures within the same university. So you have to, you know, really check what the particular department, what kind of structure they have. But it's not for you to choose, right? So the department will tell you what their structure is.
Okay, another question in this direction. In the UK, is there also a central hub, I guess a mailing list where one could find open postdoc positions or?
Yeah, there's the Jobs AC UK website. Maybe I should add this to my slide. I can add it to the slide, and then you can post it on the webpage.
And you can just write it in the chat right now for our audience.
Okay.
You already go there and check.
Okay, but I should say that many of the UK positions also go via the STNet website, which was already mentioned, right? This is not restricted to German positions. This is really for many European and other positions. So this is personally a website I personally use a lot, and I recommend to all my PhD students and postdocs, right? So yeah.
Okay, so that's the first question. Almut, what do you think is going to happen this year or next year due to the economic crisis?
Yeah, so I mean, obviously, I mean, the answer is I really don't know, but if I should speculate a little bit, the situation is very similar to what was described now for Germany, that so far we don't see an immediate change, right? I mean, funding is there, people can apply for grants and so on. There was obviously, you know, a lot of, you know, talk about hiring freezes and things like that. But then also, I mean, some of you might have heard there was this U-turn of the UK government that the A-level results were revised, and this caused now a last-minute changes of student numbers for many universities, and the UK universities obviously rely heavily on income from international students. So we have to see now how all of this evolves over the next couple of months. But it seems like some universities will get significantly more students than what we expected. So, I mean, initially, you know, it was announced there wouldn't be any hirings, and now immediately, like we have now already immediately advertised a position to help us to actually make it through the next academic year, because we expect more students. So these positions are at the teaching fellow level. And when it comes to grants, yeah, I would also expect that for the time being, it's kind of the same. People can apply, but obviously the minute, you know, the economic situation gets worse, I would also expect that there will be, it might be less likely to get these grants, right? If the funding gets reduced, it's just getting more competitive, right? I think that's the thing. You can probably always apply, but the level of competition gets higher. That would be kind of my expectation. But at the moment, it's almost business as usual. So people should apply and should obviously get in touch with, you know, academics at the university they would like to apply to, and also get some advice on, you know, the applications and so on. I think that would be helpful.
So it's always important networking also to get a postdoc position or
yes, and to
a PhD in the UK. I guess this is also a little bit for every postdoc position, a little bit of networking and knowing the professor, the work, and in what you are really interested in.
yes, exactly. Just also to find out if you come out of a different system, right? So that you get advice on, you know, what's expected. So as I said, you could apply for lectureship straight away, but often people would have maybe at least a year of postdoctoral experience, right? But also I would say you would then really, you should apply then for lectureship. You should not wait, you know, to go for 5 to 10 years of postdoc before you apply for lectureship. You should really go for it and see how it goes, essentially.
Okay, Ahmed, thank you very much. Let's pass then to our next speaker, is Olivier Winterberg, professor in applied mathematics at Université Paris et Marie Curie in Paris. So he will speak to us about the French hiring system. Okay. Olivier, can you hear us? Ah, yes, okay. The floor is yours. We don't hear you. Now we hear you. Okay.
Yeah. Okay. So,
perfect.
So thank you very much, and it's a pleasure to be part of this discussion. And I will talk about the specificities of the French system. I would like to say that the mainstream in the French system is quite inflexible and didn't change for a long time. That's very specific. It's called maître de conférence. I would say that it's equivalent to assistant professorship, but you get it right after your PhD. This is a civil servant job in the sense that you have a 100% job security. You are hired for your whole life by the state, by the government, through a university. And let's say that last year in statistics, you had something like 15 positions open and a bit less than 10 in probability. So I don't think that the COVID will change anything about this system, which is, as I said, quite inflexible and simply depend on the number of people who go to retirement the year before, and so that's continuing in this way, I would say. And the salary is not that competitive with other positions elsewhere, but as I said, you have a job security, and you have teaching duties, of course, during the year. So to get this position, it's quite a long path. First, the fact that it's for civil servants, so it's restricted to EU citizens only. Then also you need to be qualified for applying to this position. The qualification is given by a national committee, and you need to produce a CV and to send also things that can be a bit complicated for foreign people, like translation of all your diploma in French and official translations. So you have to be a bit careful about it, because it's also mandatory for applying. And the deadline is already in December, so beginning of December. And it would be nice to show already in that step, in these former steps, that you have some ability to speak French. Because as you have teaching duties, you may know that most of the teaching in France are in French. So it's likely that, even if it's nowhere written explicitly, that you need to be fluent in French to get the position. Okay, then the job descriptions are posted in the spring. So the idea is that you have a calendar, a national calendar, and then you apply only to local positions, depending so each university have a position, and depending, of course, on the profile of the position. And then you get a local ranking on that position, and then basically the rankings are posted online, and so you can have different choice, and at the end of the game, the third, let's say the one that is ranked third can get the position simply because of the two first one choose something else. Okay, so that's something typically French, and now I will go to other typical civil servant positions, but for researchers. So for researchers, you have few civil servant, so life for life positions, and they are from different institutes. So you have the CNRS, which offers around 10 research positions in maths, so it's quite theoretical. It's also widely open to EU citizens that may not speak French, but you need to really have a very competitive, I would say, CV. And it's the same for INRIA. So you have something like 10 researchers in computer science, 10 positions that, so in computer science, related to computer science, but that are open to, let's say, statisticians. And then you have also INRA, where there it's applied statistics, so applied statistics to environment, to climate, and so on. And again, these positions are likely to be open to EU citizens that could not speak French. And they are, as I said, they are quite competitive, and so that's national ranking, and then you get the position depending on your rank. So now there are also different things at university which are called grandes écoles. Grandes écoles, I have done a grande école myself, as most of the researchers in France. They are basically very competitive programs and restricted to few students. And I would say that there the jobs are more flexible than the maître de conférence. And but the environment can be quite excellent, like Polytechnique, and so you have very high center in applied mathematics. And so for most of them, most of the positions, they are much more flexible in the sense that you may not be a civil servant, you don't need to be qualified, you have no official calendar, and the salary can be negotiated, and also your teaching duties. And for that positions, you may go directly to the websites of the different grandes écoles. And then for the non-permanent positions, it's something brand new for France, so it's a way for us to go to be closer to the other systems. And some are limited to foreign applicants. So I would say that for non-French students, it's a good way to start and to come to the French system. And so there, how it works, most of them are not, I mean, even all of them are not funded by universities, but by other institutes that are funding postdocs in a group of universities. So FSMP, for instance, is for the group of universities of the center of Paris. Adama is for the group of universities of the south of Paris. So the suburb of Paris. And there you have positions, postdoc positions for limited to foreign applicants. And you need the name of the postdoc to get funded. So in some way, I recommend people who would be interested to directly contact one professor in one of the universities within the group of the subsidized by these institutes, and then directly ask to him if it would be likely and it would be willing to support your application for a postdoc. And then you have a the old system was very specific and it's ATER, and so it's a position which is limited to 1 year, and with teaching duties, and which is done for basically finishing the PhD, and so it's I think more limited for French PhD students who require 1 extra year after the 3 years to finish their PhD. Okay, but fortunately, the Society of Applied Mathematics know that it's quite a complicated system, and you have a lot of the offered positions that are in their website. So it's called Opération Poste. It's in French only, but it's very useful. And so you have a login and a password to enter into the system, but you may guess what will be the password for the next year. So everybody in France knows the login and the password. So I encourage you to visit this website by updating the password for next year and see all the positions that are offered in France. Okay, thank you.
Thank you, Olivier. A question that actually comes a little bit from the chat, connected to something the guys asked in the chat already. I mean, when you talk about the program for researchers in France, so without teaching duties, what you said it has to be excellent, it's very competitive. Could you quantify for us a little bit in terms of number of publications, if possible? Which kind of curriculum or portfolio a student should have in order to just start thinking about applying to, for example, a researcher position?
Okay, well, I would say that for CNRS, you really need to have publications in top journals and theoretical ones for getting a position in math. Then you have also every year 2 or 3 multidisciplinary positions, and there the profile is more specific. And if you enter exactly into the profile of this multidisciplinary, most of them are math computer sciences, then it could be easier to enter in the CNRS, but you still need to get a very high CV with top publications. For INRIA, it's the same. For INRA, you have profiles. So there, it really depends, again, if you are into the profile, then it's easier. For INRIA, for most of it, the profile of the position is very broad, and so the competition is very high and really depend on the list of your publication, I would say, and the list of the publications of the other applicants.
And let us say it has to be substantial, so not just one publication is not enough. Let's say
for an example
for the audience. Or...
not for sure. For CNRS, everybody in France is applying to CNRS. Everybody in maths, more or less, every PhD. So you have to be competitive with the top 10 PhD students in France. It means more than 5 publications in top journal, I would say.
Okay, thank you, Olivier. Can I ask you to answer to the question that is in the chat, because we have to pass to the next speaker, and so we all read it, and in the meantime, we pass to our first speaker, Giulia Di Nunno. She's professor of physical stochastics at the University of Oslo. So she will speak about the Norwegian system, and perhaps she can give us a little bit an overview on how is the hiring system in the northern stage of Europe. Perfect. Okay.
Hello.
Yeah, the floor is yours.
Yes, thank you very much. I'm trying to put a full screen. Is it fine? Can you see that?
Yes, we can see it.
Yes, okay. So thank you very much also for having the opportunity to present what's going on in the north of Europe. And it's a great opportunity to see also the differences with the different systems that are so surprisingly different sometimes. But the Scandinavian countries are very small countries compared to Germany and France and UK and the big shot countries in the Central Europe. And we hear more from Italy and Spain afterwards, so the same. So let me say that when I talk about Scandinavian countries, we are talking about populations that range from 5 million people to 10 million people, everybody counted. So comparatively, we have a very few full universities, and I can actually list all the universities in Norway. They come here, and in Denmark and Sweden. So as you see, they stay in few lines, but there are many more university colleges. And the main difference is that a university is research-oriented in the whole of its activities. So it's pushing on research, internationalization, and research-oriented teaching. While university colleges have a little bit of different orientation. Sometimes they are oriented to specific type of educations, and sometimes they are oriented more to a kind of teaching format. But nevertheless, in the recent years, after some strategic decisions at the ministry, all universities and university colleges have to move to a more research-oriented direction. So when looking for jobs, also university colleges can have competitive positions, even though typically with more teaching duties. So this said, I will say a little bit about the structure of the academic positions, which is actually a little different between the three countries of Norway, Denmark, and Sweden. And I have more specifics on Norway being there. But all of them have a postdocs to start with. And for postdocs, a PhD has to be completed. And all these postdocs, this is pretty much similar in the three countries. They can be funded by the very university. And in this case, they may entail, but only may entail, some teaching duties. Or they can be funded by research projects. And research projects themselves are funded by different institutions. In Norway, this would be the Research Council of Norway, for example, or European funded projects. In Sweden, there are also some other funding possibilities coming from foundations, for example. But anyway, usually this is clearly stated in the advertisement. And these postdoc positions can vary from 2 years to 3 years. But also, if there are teaching duties, this would be specified. And typically, a teaching duty is quantified with a longer period of postdoc position. So the formulation would maybe be something like 2 years postdoc position plus 1 year dedicated to teaching duties, which doesn't mean that this 1 year is only teaching duty. It will be spread over the 3 years anyway. So it's usually very well written in the advertising, in the calls. But then you have the standard research track, which would bring from a postdoc, which is a temporary position, to associate professor or førsteamanuensis in Norway. And this one, associate professor, is a fixed position. So this is the real first position. There is no assistant professorship in Norway, for example. But that's different in Denmark and Sweden, where you have an intermediary junior position, which is a fixed position. So typically called, here I read, assistant professor or junior lecturer or things of similar sorts. And those positions are open by call, and there is a competition for application. And then there is a system of promotion that has been already pretty much described similarly by others in other states. And the promotion in Norway, for example, from associate professor to professor is typically based on a national committee who is relying on international referees. So there are no fixed dates for these positions to be announced. Everything comes up. Also postdoc positions that we don't have fixed dates. So it's I think pretty engaging in the sense of one needs to follow up what's going on. In Norway, in the recent years, just because there was such a big gap between postdoc and associate professors, they have experimented, and we have a couple in our department running very well, a tenure track associate professor position. So this was a kind of advanced postdoc position that after a few years has to be evaluated. And if evaluation is positive, then this turns into a complete associate professorships. And so this is a new trend. No one so far has arrived to the evaluation time. So I cannot answer this level, they are so new. But they seem to be very promising, and they are quite competitive, I must admit, to enter. There is also a kind of teaching track, and this one is typical or more typical in university colleges. I must admit that in mathematics and statistics is not really common, this teaching track. It's usually research-oriented tracks that are proposed in the calls. But in some university colleges where maybe mathematics is more of a support basic knowledge, and then a lot of teaching is necessary, then lecturer and then senior lecturers are proposed. And so then it becomes a different kind of career path, but there is improvement in positions, and there is a career as well. Denmark and Sweden, pretty much there is this usual structure. As I said, there is a little bit of, there is an extra step. In Denmark is this assistant professor, which can be permanent, temporary, or tenured, depending on the call. So maybe the tenure has become a little bit more popular in the very recent years, but difficult to say. And Sweden has also the same situation, where there are some lecturer positions that have quite a big chunk percentage of teaching. The interesting aspect of Sweden is that to be associate professor, one needs to have a docent title. Docent title is a bit like habilitation in Germany. People applying from outside implicitly will be evaluated if their CV has the same kind of parameters of a docent title. And the same happens in Norway. It's not explicit, but to be associate professor, that would be the implicit request in reality. Because this docent is what brings people to be able to supervise PhD students, basically. Okay, so this said for general academic positions, let me say something about language, because in the Scandinavian countries, everybody speaks English, but we have national languages, and that's Norwegian and Swedish and Danish. Typically, in the announcement, it's written, if any language is requested, they would say Scandinavian language. They wouldn't require a specification on any of them. In Norway, they wouldn't say you have to speak Norwegian, but they would say it's Scandinavian language, because they're quite similar to each other. But I want to be very clear that any academic position in research is not based on the knowledge of language. They are all based on academic parameters, research quality, teaching experience, activities in general, and general CV. So you don't need to know the language a priori. But if you have a fixed position, then there will be a requirement to learn the language in a few years from start to a reasonable level. Mathematics is particular, and statistics goes the same, it's particularly internationally based. So maybe there is a bit more flexibility in what level is required. But nevertheless, this is something that it's usually written in the announcements. Completely different could be for teaching positions, because typically teaching positions then require some knowledge. And as you see, many of our master courses are actually possible to be taught in English. And actually it's required that lecturers provide courses in English. We have a very international participation of students, Erasmus students, exchange students, etc. So they all are not required to know Scandinavian languages, which are not probably mainstream in many programs. So, but when teaching at very first 2 years, then that is a bit necessary to know Norwegian or Danish or Swedish. That's pretty much similar in all of these countries. Now, other institutions provide research positions.
Yeah, just 1 other minute.
Yeah, and this is Statistic Bureau, Statistic in Norway, the Norwegian Central Bank, SINTEF, and the Norwegian Computing Centers, just to name some. And these are all interested in probability, statistics, analysis, and mathematics. Also in the private market, there is need for PhDs, and sometimes they entail some research, but here it's really minor. And in particular, maybe in the supervisory authorities and the Norwegian Central Bank, in particular in the section of the fund, the Norwegian Pension Fund. These are the important websites, so you can read them later. Jobb Norge and Jobb Safari for basically all positions, but positions in Norway are announced internationally on all mailing lists, though that is possibly less coordinated, but again, STNet is used, for example, and also Bachelier Society, and there are some other sub inside the Bernoulli societies, etc. And then what can I say? In Norway, there are no dates. So every position can be opened any moment. So stay on your toes if you're interested, because there is no particular scheme to rely on. Thank you.
Thank you, Julia. So are there any questions from the audience? If not, I have a small question. So do you think, it's always the same question, it's the spirit of this meeting. Do you think there are going to be any change in the call in the next year or this year due to the economic crisis?
A little similar to everybody else. I have to say that the moment is business as usual. We have calls coming up, many according to projects, and there are going to be open calls for projects. So after the calls for projects, there will be calls for positions. And it doesn't seem that there is going to be much of a change, really. It's possible that with the crisis and the Norwegian crown being linked to oil in particular, maybe some reductions could be expected. But at the moment, it doesn't really seem so. So at least in the next 2, 3, 4 years, that seems that we are still running.
Perfect. Good to know. Thank you, Julia. If you have some questions from Julia, just post them in the chat, and Julia, give a look at it in the case someone is asking questions to you. Let's pass in the meantime to the next speaker. She's Marta Sansolé. She's professor of probability at University of Barcelona in Spain. She's been also the president of the European Mathematical Society from 2011 to 2014, and it's here today to explain to us the hiring system in Spain. So thank you for coming, and the floor is yours.
Thank you very much, Imma. I am very pleased to be here with you, and also congratulations for the job, the task of the Young Researchers Committee. I think that this is a very important place and at the service of the young community of researchers. So I will be much more schematic than my predecessors because, well, our system is quite complex, I guess, as everywhere. And I will focus on, as I was asked to do, job opportunities after PhD, okay? And so essentially the academic path. So the postdoc positions are, so the calls are published, funded, and evaluated by the following bodies. So there is the State Research Council here. So then there are also state research councils from the autonomous governments. To the best of my knowledge, only in Catalonia and in the Basque Country. And then there are private foundations, important private foundations, mainly La Caixa. La Caixa is a financial.
Sorry, Marta, we don't see your slide running.
You don't see my slide running?
No,
okay.
We see them steady. We don't follow.
Okay, so that's very bad. So I think that what I have to do is to stop share and start again. So I will do that because this happens to me last time. Yeah. So let's try if now it works. I am sorry about that. So you see the first one now?
First one, yes.
And the
second.
And the second one, the third one?
Yes, it runs now.
Okay, so it's a matter of trying twice. Okay, so I will start with the postdoc positions. So the postdoc positions are, so the call is published, is funded, and it's evaluated by the following bodies mainly. So there is the State Research Council. So this is so for all Spain. Then there are research councils in 2 autonomous governments. This is in the Basque Country and in Catalonia. So of course it's much more limited in number, but we have that. Then there are private foundations, mainly La Caixa, which is a financial institution. And then there are 2 centers of excellence in mathematics. One is the ICIMAT in Madrid, and the second one is the BECAM in the Basque Country. And finally, the math departments and institute. So why I put some of them in green and some of them in orange. So this is because, so the difference is that these centers of excellence in the math departments, they publish calls, etc., but they are also host institutions. So this makes a very big difference. So there are also host institutions. Okay, so then essentially, so these postdoc positions have yearly calls and more or less at fixed dates. For example, for the central government, this is in November, December, etc., etc. So I will not give the details, but they are more or less fixed. And we have 2 types also essentially. There is, so this is very schematic, as I said. So there are the retaining type and the incoming type. So retaining means to retain talent. So one of the requirements is that the applicant has a PhD awarded by a Spanish university or academic institution, while incoming is more to attract external talent, so they can be foreign people or people that move to postdoc first to a foreign country and so on. The duration depends on the type of postdoc because there is a variety. So mostly there are 2 or 3 years, so the official calls for the green blocks, except one which can go up to 5 years, and this is a kind of tenure track postdoc position, which owes the name of the neurophysiologist, neuroscientist Ramon y Cajal. So the regulations, well, more or less are similar, except that in the calls of the autonomous governments and of the La Caixa, of these private foundation and other foundations, some of them are partially supported by European Union programs. Mostly the COFUN program, and therefore all the European Union mobility rules apply. Okay, mobility rules and also the essential rules of the Marie Curie fellowships. So then, as I said, concerning the orange blocks, so the research centers and math departments, they host and they publish calls. The difference is that the calls they publish are much more limited in number, and they are focused. This is because so BECAM and ICIMAD are funded by excellent research projects that are, so to say, topic oriented. So they are large in the scope, but nevertheless, they are topic oriented. And also a difference between also these calls and the calls from the green blocks are that in general they are much more flexible, both in eligibility and duration. Okay, so of course, maths department is in principle free to call for a postdoc of 1 year only or something like that, research oriented, etc., etc. So this is more or less the picture. So now when we go towards a permanent position in academia, there are also 2 parallel career paths, one much larger than the second one. So one is the state career path, so for all Spain, and this is very much the same as in France, and this is very natural to understand because it was actually brought from France when well, it was a gift of the Bourbons when they came to Spain in the 18th century. So it's almost the same. With some variants that have been set up in the recent years. So there are non-permanent positions, so assistant professor, all with PhD, all required a PhD, and lecturer. And then there are permanent positions, which so they bring together the civil servant status, and there are 2 types. So associate professor, like the maître de conférence in France, and full professor is so full professors. So to apply to each one of these possibilities, there is a requirement, as has been said also for other countries. So there is a certification of eligibility. That means that so this says that you are qualified to apply, and this certification is delivered by a state or regional evaluation agencies. So there are committees depending. So each one for each topic, I would say, or discipline. So one in maths, etc., etc. So this is the career path. So in Catalonia we have in Catalonia we have an alternative career path, which is tenure track. So the state career path is non-tenure track. So this is the way it is. So in Catalonia, we have the Serra Hunter program, which is funded by the autonomous government. And the first step is a lecturer, which is tenure track eligible. So there is an evaluation after 5 years. And then there is the possibility of promotion to associate and full professor permanent. And we are not, so the people that go through this track, they are not, they don't become civil servants. So all the calls are completely open, and so there is an open competition, and a specific committee for each one, etc., etc. So it's completely open. So then outside the academia, as was also mentioned by Julia, I think, so most of our graduate people go to outside the academia. So in fact, the possibility to stay in the academia is quite restricted. So specifically there are many opportunities related with finance, statistics, IT, etc., and including industrial mathematics at large. But this sector of industrial mathematics is very much related with mathematical institutes, I would say. So while the others are companies or financial institutions, etc., etc. Okay, so this is the picture, and well, we were asked also to say something about the impact of the COVID crisis. And of course, I think that we all are very worried about that, and stimulate a lot of thinking. So at present, so the history is very short, so there are only 4 or 5 months at most. So one thing that in my opinion has been positive, so I put here green, orange, and red. So the green part, so the positive part, is that very fast there have been specific research programs funded by the state focused on COVID-oriented research. So this, of course, for the moment, there have been very few mathematicians involved, more specifically statisticians and also people from computer science, but nevertheless they are there, and this is opening a nice possibility. There have been some delays in the calls, and more than in the calls, in publishing the results of the calls. So this is natural, but it has not been dramatic so far, so a month, something like that. But talking with the directors of the two main institutes, ICIMAT and BECAM, they both agree in that they had quite a lot of difficulties in helping the new hired researchers to settle in the new place. So of course there is a lot of uncertainty, and so this is a problem, and also a perturbation of the working dynamics. So of course we find very nice now to see all of you through this screen, but at the long term, I think that this is. I don't know, I wouldn't say a catastrophe, but it's not the right way to work, okay? So this is really bad. So now concerning the future, of course, it depends very much on whether this crisis lasts 2 years or 5 years, so one doesn't know at the moment. It's clear that there is a correlation between the sanitary and financial crisis. However, I think that the impact in budgets for research may be not so dramatic. So maybe the impact will be very, very high in many sectors. So we are seeing that. But in research, we are in a sort of bubble, privileged bubble. And I think that since the crisis has shown the crucial role of mathematical sciences, so we see in the journals, on television, everywhere, so scientists, mathematicians and physicists telling us the models, etc., etc. So this could be, I mean, maybe the impact will not be so high, at least at the short term, okay?
Sorry, Marta, we have to wrap up.
Okay, so then new opportunities, as I said before, and of course on the bad side, there is so the question of mobility, which is one of the pillars of the European research area. So now it's in danger and a lot of uncertainty. Nevertheless, I think, like Julia say, we have to stay focused, be patient, and never give up. So thank you very much, and I am sorry to have taken more time than I expected. Sorry.
Thank you. We have just as question, very small answer is possible to this question. Florian asked how important is knowing Spanish or the local Basque language at the time of application for postdoc or other.
Compulsory?
So how important is knowing Spanish?
Yeah. Okay. So at the level of postdoc position, this is not important at all. So the situation is a little bit similar as in Norway. Okay, so for teaching, yes, at the undergraduate level, you have to be fluent in the language, but at the postdoc level, there is no requirement about that.
Okay, thank you very much. We have now our last speaker. He is Claudio Fontana, a senior lecturer in the Department of Mathematics at the University of Padova, and he will explain to us the hiring system in Italy.
Yes. So thank you very much, Ima, for the invitation to participate to this meeting. I think it's very useful and a great idea to organize this kind of roundtables. So let me start with the presentation. So I'll focus on the academic career path in Italy. And like in many other countries, this is divided in 3 main steps. So the first one, just after the PhD, is the postdoc, which in Italy is called assegno di ricerca. Then the next natural step is the assistant professor, which in Italy is called ricercatore. And then, of course, you have associate and full professors, which are called professore associato and ordinario, respectively. So a few general aspects about working in the academia in Italy. So all academic positions are fragmented into many scientific sectors. So many other countries like France have also scientific sectors, but the specificity in Italy is that they are quite small sectors. So for example, for people working in probability, you have Math 06, which is probability theory, mathematical statistics, but also a different sector, which you see here, which is typically for people working in mathematical finance and applications to insurance and other social sciences. So other few points to highlight is that in order to become associate or full professor, you need to have a specific national scientific habilitation, which is known under the acronym ASN. The exception is for direct calls for foreign researchers. If you come from a foreign institution, you can avoid and obtain an equivalent habilitation which replaces this ASN. So most of the academic jobs in Italy are at universities. There is also the Consiglio Nazionale delle Ricerche, but this accounts for a very tiny fraction of all academic jobs in Italy. So in terms of salaries in general, so at all levels, for all positions, they are typically lower than in many other European countries. But you have to keep in mind 2 important things. First, if compared to other countries, life is usually cheaper in Italy. And more importantly, there are very significant fiscal incentives if you come from a foreign institution. So concerning the first one, so postdoc possibilities, here I would say everything is possible in the sense that the duration can be 1, 2, 3 years. They are funded either by specific projects or directly by university. There is no fixed calendar, and the best way to stay tuned on postdoc positions and opportunities in Italy is to subscribe to one of the mailing lists that I will show you at the end of this presentation. So I will pass now to the presentation of assistant professorships, which are always fixed-term positions. So they are always fixed-term contracts. And they come into two different types. So there is the type A, assistant professor, and the type B, assistant professor. The main difference is that type A is like a junior assistant professor, type B is senior. The first one is purely a fixed-term contract for 3 + 2 years, with no possibility of renewal at the contract expiry. And the key difference is that for type B, this is a fixed contract for 3 years, but with the important difference that it comes automatically with a tenure track system. So it means that at the end of those 3 years, if in the meanwhile you obtain the scientific habilitation, you essentially get an automatic promotion to the level of associate professor, which is then a permanent position at the university. So the tenure track system in Italy is now embedded in this type B assistant professorship. Now, my only comment which relates to the impact of COVID, of course, all the general remarks and observations that were made in the previous talks also apply to Italy. I can say that from my perspective, at least what I can say from my university, the University of Padua, is that the offer of type B assistant professorships is expected to stay stable at least for the next 2-3 years. So there will be a constant number of type B positions, also because the government just increased the number of positions in response to the COVID pandemic. So the important thing to keep in mind is that for type B assistant professorship, which is obviously the most attractive one, the key feature is this scientific habilitation. Now, what about this habilitation? So it is necessary in order to get the promotion to the level of associate professor, and it is specific for a scientific sector. For example, if you work in mathematics for economics, or if you work in probability theory, then you will need different scientific habilitations. The habilitation itself only depends on your CV and track record of publications, again, specifically for each scientific sector. And since, okay, we are here at an international conference, it is important to remark that if you hold an equivalent position at a foreign institution, you may be directly eligible for a position at the level of associate professor. And currently, this is very much incentivized in Italy because the university essentially pay less for your salary if you can be recruited through this scheme. And here is the webpage where you can find all the relevant information. Then a second opportunity which can be interesting for people working abroad is the Rita Levi-Montalcini program, which is a very competitive program. The nice feature about this program is that you can submit a research proposal. You choose the university, so any university in Italy, and if then your proposal is evaluated very well, then you obtain a type B associate professor in the university of your choice, together with a research fund.
Claudio, we don't see anymore your slide, I guess.
I'm sorry for that.
I guess we lost it.
Where is it? Do you see it now? Can you see the slides now?
Yes.
Yes.
Okay, thank you. So the last point here is about fiscal incentives for people working at foreign institutions. So here the main requirement is that you have been active in teaching or research at a foreign institution for the last 2 years or more, of course. The basic advantage is quite substantial. So if you get a job at an Italian university, 90% of your income is tax-free for 6 years. And those 6 years can be extended if you have children or if you buy an apartment in Italy, etc. So this scheme is applicable to all positions starting from the level of assistant professors. So this is not applicable to the postdoc positions. It is applicable to type A and also to type B assistant professorships. So let me continue. Just a bit of advertisement about what is going on specifically at my home institution, the University of Padova. So there is a nice scheme, which is the Marie Curie Action Seal of Excellence. So you know that you can apply to this wonderful Marie Curie scheme of the European Union. If you select the University of Padova as host institution, if your proposal is very good, but not good enough to be funded by the European Union, and you receive this seal of excellence, then the University of Padova offers you, as a replacement to the Marie Curie Fellowship, a 2-year research fellowship contract with a very good salary and research fund. Then, at this precise moment, my department is also looking for people interested in direct calls at the level of associate and full professor positions in any area of mathematics. And finally, let me make this specific advertisement. So I'm also looking for a postdoc in mathematical finance starting next year. So to finish, here are just some web pages where you can find all the relevant information. So the first one, in this website, you can find all the official documentations on how does it work, the academic path in Italy. So you find all the details about the scientific habilitation, direct calls for foreign researchers, etc. The specific calls can be found on the second webpage, this bandi.mur.it. So here you can find all the open and closed calls for all positions, so including postdocs and assistant professorships and whatsoever at all Italian universities. And finally, to stay tuned about what is going on the Italian job market, in probability, the best that you can do is to subscribe to the random mailing list. So this contains announcements of open position, postdocs, workshops, and seminars taking place in Italy. And of course, if at any point you need any specific information, you are welcome to contact me at my email address here. Okay, this is everything I wanted to tell you. And again, many thanks for this opportunity.
Thank you. Thank you, Claudio. I have a question for you, and it's also going to be the last question for also all the other participants to this roundtable. How many they asked me to quantify, so how many publications are expected from a PhD student to take a postdoc position in Italy, for example?
Well, I would say that it depends very much on how competitive the selection is, the number of potential candidates. But typically, so a postdoc is targeted at very young researchers. So in my view, typically even 1 or 2 good publications, not necessarily in top journals, but good publications are typically enough. But then also, okay, you have to keep in mind that postdoc positions are typically very specific. So typically they are funded within a specific research program. So of course, the candidate has to be very well aligned with the goals this research project.
Thank you, Claudio. Can I ask you to answer the question of Jonas in the chat? And in the meantime, we ask speakers about the same question. So we speak just about a postdoc position. So let's start from Stefan. How many publications do you think are necessary for a PhD student to get a postdoc position in Germany?
Oh, well, I mean, a postdoc position might be anything after completing the PhD. So the standard that you have, I mean, then you just submit it, and then, well, it depends on the field, like, and also on the requirements of the project that is related to it, perhaps. There's no necessary criterion that you have to fit into.
Thank you. Okay, what about in UK?
There is no fixed number. It could be anything from 0 upwards. So it's a postdoc position is right after the PhD. So obviously you would hope that the PhD student has maybe submitted. So if there's a revise and resubmit to a top journal, that would already look very, very good. So yeah, so in principle, somebody could get a postdoc position without any publications, but it depends on the competition, right? So if there are obviously older people applying with, you know, a more significant publication list, then there might be more competitive. But I've seen it that, you know, younger researchers with no publications have been judged more promising than, you know, an older researcher. So it really depends on the case. There's no fixed number. So, you know, if you're a promising candidate, you should just apply. That's the general advice, no matter how many publications you actually have.
Perfect. So the problem is just in France, Olivier. They have to have a lot of publications.
No, not for postdoc. Not for postdoc.
Not for postdoc.
No, not for postdoc. For postdoc, it's. I think it's it's also quite open, and I think what's really important is a good match with some so the professor who will push your project and your application in the program. So in order to found the position in his university. So it's really much more open for postdoc, and it's exactly the same than in other European country. The specificity was for CNRS that it's quite competitive, especially for foreign students, and basically it's one way for France to get field medalists. So it's it gives you the rate of competition in this.
Yeah, we are all very scared at this moment.
May I say something? May I say something? Okay, so in my opinion, it's more a matter of quality than of quantity. And this is not only at the postdoc level, but also at the level of a permanent position. So because the number of publications vary very much from one subject to another. So in the case of postdoc positions, of course, it's important to have some publications, and also the quality depending on the journals. But something that, in my opinion, is important. I am not talking about Spain, but in general, is the research project of the candidate, because the research project shows the maturity, you know, and also so if the candidate has a good or I don't know how to explain that. So it's determined to discover something. You know, when you see the research projects, or why they have applied, what is the reason why they applied. You see the personality, you see also the abilities, you see many things. So of course, I mean, publications are important, but I would say that the number depends very much on the state of your career, also on the type of postdoc and so on.
Okay, Julia, you have the last answer.
But I agree with everybody. In as a postdoc, it goes from PhD just after to maybe if it is a second round postdoc, there is more experienced people that can apply. So what is particularly searched typically is quality, as Marta says, but also the kind of prediction that the evaluator in committee does of the candidate in how good can fit into the position, what it can be the progression in the future of the person participating. So sometimes the committee is asked to look into the future and to see the potentiality of the person. But of course, there is also a difference that was already mentioned. If a postdocs are specific in a certain project, possibly the research project is dominating the requirements of the CV of the candidates. So people would be asked to join a certain research group to a certain extent. And then this one could determine a little bit what quantity and quality means. If the postdoc position is really open, then of course that it becomes a tougher competition to a certain extent, but also more maybe open to the personal development in the different research directions. So it's very difficult to give a rule. And it is a competition meta. The best is to apply. No application, no gain anyway. So if a person is reasonably fitting and thinks he's ready, then the best is to apply.
Thank you very much. Thank you very much. I would like to invite you all, if you have still a little bit of time, and also our audience, to join us in the coffee garden, where we can also have a really conversation with microphone and video. I don't know if you guys have already used this tool of the conference. For the people that leave, first of all, let's thank our speakers. You've been really great in sharing with us all this information. Really, sometimes it's difficult to figure it out, this jungle of our system. So thank you very much for your clarity and your participation in this event. I want also to thank my fellow colleagues of the Young Research Committee and the IMS Young Researchers Committee, with whom together we have organized this big event, virtual event during the conference. And I would like to tell all our audience that if you guys are interested to follow the activity of the Young Researchers Committee of the Bernoulli Society, to join the Bernoulli Society, okay? Remember, for PhD students, the fee to join the society is completely free. So thank you again for participating, and we hope to see each other again, perhaps in person soon, the next conference. Bye.
Bye.
Bye, everyone.
Bye.
Am I allowed to just say one more word?
Yes.
Because I think with this COVID, we had like negative points concerning COVID, and certainly it's very bad to have that. There are also some positive points that I would really like to stress here. Namely, we changed the interview system to more or less Zoom interviews. So nowadays, it's much easier to fly somewhere, whether in the UK or in Oslo or in Germany or in France, even if you are in Australia or Japan or in the US. So it's much easier. So in earlier times, we had really to think hard whether we invite people, because it's quite a lot of work to do, and it's also very expensive. And now it's very cheap to do that, and we do that. So it's also a big chance for people and to get more international. So it's not only less mobility, it's also more mobility, at least at that point. Yeah.
Absolutely. Guys, you have just to apply for postdoc positions in Europe if you want to, and try. As many applications you do, more chances you have, statistically speaking. So just apply. Thank you. Thank you very much to all of you.
Thank you, Emma.
Bye.
Bye.